implementation world, but I'm hoping to, oh, actually I should give the signal for start recording. Yeah. Let's wait till we have ready for recording when you are. Okay, sounds good. Yeah, so something that is mostly a research project at this point, but I'd like to, extend it to more of a machine learning system in the future. And so I'm going to talk about AI-guided experiments for ML systems, AutoML, and science. This is with a number of collaborators, a couple projects in here from different universities. As background, I'm a postdoc at Stanford, so this is with some of my collaborators at Stanford, as well as with some folks from CMU and some folks from National Lab, so the SLAC Accelerator National Laboratory that we work with. Okay, so experimentation. When I say experimentation, I view this as the process of taking actions to acquire data that's useful or informative for a given task or to estimate a given quantity. So experimentation comes up all over the place in science and engineering, from materials design, drug discovery, robotics or reinforcement learning, for example, exploration or active learning, optimizing computer systems, and more generally AutoML, things like hyperparameter optimization and neural architecture search. A lot of the work in this area involves sort of topics or fields such as active learning from the machine learning community, optimal experimental design from statistics, as well as generally a broad set of Bayesian methods. And the thing that I want to talk about today is a new framework that I've been working on for flexible experimentation, sort of broad purpose experimentation, which extends a classic method called Bayesian optimization from estimating global optima to estimating a broader set of properties that can be used in different experimentation tasks. And later, we aim to incorporate this method into a broad purpose experimentation system down the road. Okay, so, oops, wrong direction. Okay, so let me first give some background on black box global optimization. So suppose that we have a noisy black box function, which we'll call f. You can query f on an input point x from some domain, and you can observe an output y. And we're going to assume that observations are noisy. So the observation y that you observe is a noisy version of f applied to a given x. That each function query is costly, for example, in money, time, human labor, or otherwise to do an evaluation. And the goal of this task is essentially to estimate the location of a global optima of f within a limited budget of queries, let's say within a budget of capital T queries. So there's many different applications of black box global optimization in different areas. A couple of which I mentioned a second ago. So in AutoML, hyperparameter optimization and neural architecture search sort of classically has been framed as a task of black box global optimization. Systems auto-tuning, for example, in databases or web servers, some projects in industry that are using black box optimization for these kinds of tuning tasks. In the sciences, in national labs, there's been a lot of work on optimizing laboratory equipment and machines, such as in the accelerator space or in tokamaks in the plasma fusion world, as well as materials discovery and protocols. So a couple of the figures I have up here is for using these methods for catalyst design or for battery charging protocols to get better performance out of certain batteries based on how you charge them. So a popular method for carrying out black box global optimization is known as Bayesian optimization, or BO. This leverages a probabilistic model of f to sequentially choose a set of queries of the black box function, where this model basically can incorporate prior beliefs about f, for example, its smoothness or maybe other properties, to tell us where we're certain versus uncertain about the value of the function. And you can use this uncertainty for sample efficient optimization to essentially plan out a sequence of queries that are informative for quickly doing black box optimization. But the goal of this project is basically in a number of real world tasks, there's a variety of other properties beyond just global optima of a function that you might want to estimate that are useful for different tasks. So let me just walk through a quick list rather quickly here. So there's first of all different variants of optima that you might want to estimate in addition to a global optima. For example, you might care about a local optima with respect to some initialization point. You might care about the top k optima of a function if you want multiple optima that are, for example, diverse. In multi-objective optimization, we actually care about estimating a property which is a Pareto frontier of a multi-objective landscape rather than a single global optima. In level set estimation, we care about sub-level sets or super-level sets. So this is a subset of your domain whose value under the function is above or below some threshold that you define. In search task, we care about finding a subset of your domain that has value that matches some criteria. Phase identification, you care about estimating boundaries or partitions of a black box function. In some tasks, you might care about estimating roots. Quadrature, you care about estimating integrals, expectations, or averages under a black box function or a density function. You can actually view a black box function defined on graphs. You might care about estimating certain applications, properties of a graph, such as shortest paths. In sensor placement tasks, we care about finding the function value itself at a predefined set of locations. And you can even view certain aspects of reinforcement learning. If you have an unknown environment transition function or dynamics function, you can think of estimating an optimal trajectory or policy as estimating a property of a black box function. I'm going to talk about that more in a second. But the goal of this project is essentially to develop a method to estimate a broad set of function properties within a limited budget using probabilistic models. So you can view this as a generalization of Bayesian optimization to other function properties beyond global optima. So the first question here is, how do we formalize this notion of other function properties? Because it's sort of an abstract thing. So what we do in this project is we're going to define a function property with the use of an algorithm. So let me describe what I mean by that. So note that if you have a function property of interest that you want to estimate of a black box function, there often exists effective algorithms for either computing or numerically approximating this property if you were to ignore the budget constraint. So if you didn't have to do it within a limited set of queries, you just wanted to compute it, it's very cheap, there exists an algorithm that you could define to compute the function property. For example, suppose the property that you care about is a local optima with respect to some initialization point of a black box function f. You could then run some local optimization algorithm. For example, gradient descent, or the Nelder-Mead method, or an evolutionary algorithm. With essentially, I'll have the following strategy. You start at some initialization point that we assume you've pre-selected. You take a sequence of steps, essentially going downhill until you converge at some local optima, some local minimizer, and then you return the best query found so far. So this is some local optimization algorithm that isn't really sample efficient that you could apply to a black box function to compute this local optima property. Or let me give one more example. Suppose you want to compute an integral or an expectation of a black box function. What you could do is essentially apply a numerical integration algorithm, such as a rectangular or trapezoidal approximation, where you basically take the region over which you want to integrate. You can define a grid, and then over the grid, you take a query at every grid point. You compute the black box function value, and then you approximate the integral with a trapezoidal or rectangular approximation. So this is another algorithm that you could apply to a black box function to compute this integral or expectation property. So generally, I'm going to define a computable function property as the output of a given algorithm, we'll call it A, if it were run on our black box function f. So all the previous properties that I mentioned are computable function properties because there exists an algorithm that could return this property as output. Integrals, local optima, level sets, Pareto frontiers, partitions, etc. Because you could define an algorithm that returns this property. And I'm going to define the task of Bayesian algorithm execution, or BAX, as the task of estimating a computable function property, or equivalently estimating the output of this algorithm A, using only a limited budget of T queries to F, even if this algorithm A requires far more than T queries. I should also mention, if we have questions kind of during this talk, yeah, maybe a quick question.
Are there any constraints or requirements for what the algorithm could be? For example, inputs that it takes or the outputs that it produces?
Pretty general purpose. It's got the main thing is it's got to take a sequence of queries on the black box function, we're assuming. Yeah, and it's got to end in a finite amount of time. There's probably some details about the complexity of the algorithm that's important here that I haven't qualified so much. Yeah.
Just to clarify, you said, for example, Pareto frontiers, in this case, it would output a number of points that are inputs to the black box.
Yeah, it would essentially compute that Pareto frontier even in a non-sample efficient way. Yeah, so notice that we're framing a property here that we want to estimate in terms of an algorithm, right? And there's two main reasons to do that. The first thing is that it gives a flexible way to define function properties. You can slightly change the algorithm. You have a slightly different property that you've defined very, very clearly. And second of all, it's actually going to give us the procedure to do the sample efficient estimation, which I'll talk about now. So methods for BAX. I'm going to describe InfoBAX. So-called InfoBAX is what we call it, which is a method for BAX that's based on information theoretic methods for Bayesian optimization. So just as some background, There's information-based methods for Bayesian optimization, which are usually referred to as entropy search family of acquisition functions in Bayesian optimization. I'll describe them in a second. They're all based on Bayesian optimal experimental design, or BOED. And the general idea behind BOED is that suppose that you have a model with an unknown parameter of interest. You basically want to choose a sequence of experiments that most reduce the uncertainty about the parameter at each iteration, where the uncertainty is usually defined as the entropy of the posterior distribution over that parameter. So to describe this InfoBax method, I'm first going to describe information-based Bayesian optimization, then talk about how we extend it to information-based Bayesian algorithm execution. Okay, so first, just visualizing how Bayesian optimization works, and then info-based Bayesian optimization. Suppose that we have a black box function. In this case, it's a black line on the screen, defined over a one-dimensional domain X here. And suppose that we've got 6 queries of this black box function, which are these 6 black X's here. And suppose that we have a probabilistic model that we want to apply for modeling this black box function. So given these 6 queries, we can essentially visualize some probabilistic model over functions, which I'm denoting as these gray bands here. I'm showing posterior samples of the function in these colored lines here on the screen. Based on this posterior model, we can then define what's called an acquisition function. An acquisition function denoted as alpha of x, basically aims to describe the value that you would have from querying at any point in your domain. So this is something that's defined with respect to the Bayesian optimization algorithm, aims to show the benefit of what you get, like the amount of information you get from querying along any point in the domain. So what you do at each iteration in Bayesian optimization is you optimize this acquisition function after defining it to find the next point to query. And then you query this point on the real black box function. So this is the expensive query. You get a new data point, you add this to your data set, and then you iterate. So this is the algorithm I just described here. For a sequence of iterations, you optimize your acquisition function, then you query your black box function here. And the key step is really defining and optimizing this acquisition function to define a given procedure. So for information-based Bayesian optimization, what's the acquisition function? Okay, so going back to this visualization of samples from the posterior distribution over functions, for information-based Bayesian optimization, suppose that we plotted the global optima of every sample here in this pair. And I'm going to plot the global optima as a red dot. So this is the set of global optima associated with each of these posterior samples. You can actually think that there is an induced posterior distribution over global optima that's given by this probabilistic model. So really think of this as a distribution over the location on the x-axis of these red dots. Okay, so this leads us to the acquisition function for these entropy search family of BO methods, which is the following. Let me just parse this equation here. So this is the acquisition function alpha for a given input x. It's defined to be essentially the entropy or the uncertainty of the posterior distribution over these location of these global optima. So the uncertainty over the location of the distribution that you see samples of red dots here, minus the expected uncertainty of the same posterior distribution if we were to make a query at a given input x. So you can really think of this as the expected decrease in uncertainty if we were to query at a given x, the expected decrease in uncertainty over that distribution of red dots there from the previous slide. And this is known as an expected information gain, or EIG acquisition function that's used here. Yeah, so this is for information-based BO, but we're going to use a similar thing for information-based BAX. Recall that the goal is of the BAX method is basically to estimate a computable function property using a limited number of queries to our black box function, or equivalently, you can view this as estimating the output of an algorithm because there's an algorithm associated with each property. So we're going to take a similar BOED strategy here, just for some terminology. Denote the output of the algorithm A as O sub A, and we're going to care about the posterior over this output, which is P of O sub A, given a data set D. This data set D is the set of those X's, those queries that we saw before. And in particular, the entropy of this posterior over outputs of algorithms. And we're going to want to make queries to best reduce the uncertainty over the algorithm output at every step in this procedure. So we can also define an expected information gain acquisition function, which will look quite similar to the previous slide, but just with a couple terms different. So for a given x, this acquisition function is defined to be the uncertainty of the posterior distribution over algorithm outputs minus the expected uncertainty or entropy of posterior distribution over algorithm outputs if we were to make a query at a given input x. So again, this is the expected decrease in entropy of the algorithm output if we were to query the function at a given point. This is again an expected information gain acquisition function. Okay, so how do we compute and optimize this in practice? First, I need to define one more thing, which is called an execution path of a given algorithm. So I'm going to define an execution path as the sequence of queries or the sequence of XY pairs that A would have made. A is the algorithm associated with the function property, if you were to run it on your black box function. So before I describe these algorithms that you don't care about sample efficiency that's associated with a property. So take this local optimization algorithm where you initialize at some point, you go downhill until you find a local optimizer. The set of queries that this algorithm A would have made on the function that you apply it to is the execution path of this algorithm. Okay. So a couple things to, and so the pink dots basically in this slide. A couple things to note, you never know the true execution path because we're not actually going to apply this algorithm to our black box function. What we're gonna do is actually apply this to posterior samples from the black box function. However, because we're assuming here basically that the algorithm would take too many queries. It would be sample inefficient if you applied it directly to the black box function here. What we want to do is design a sequence of queries to estimate the output of this algorithm in a sample efficient way. But what we do have, we can actually consider a posterior distribution over execution paths, and that's going to be used to essentially compute this infobax acquisition function. So let me visualize this acquisition function here. Going back to this visualization before, where we have a posterior distribution over functions, where we have a number of samples drawn as these colored lines. Consider one function sample. Suppose we took our algorithm A and we applied it to this function sample. We would then get an execution path of algorithm A on the sample, which I'm just drawing an arbitrary algorithm here as this sequence of red dots. Okay, so we can actually do this for many samples and get a set of these execution paths. And you can even consider, just as before, there's a posterior distribution over execution paths that's induced by our probabilistic model. So how do we actually use this in practice to carry out the infobax acquisition function? There's two stages here that you can carry out in a pretty computationally efficient way. The first stage is before acquisition optimization, and the second stage is during acquisition optimization. So before acquisition optimization, you essentially take your probabilistic model, you take posterior samples of a function, and you run your algorithm on posterior samples to get a set of samples of execution paths. And you cache these. And then during the acquisition optimization procedure, you essentially can approximate an expected information gain value of a given input X using these cache samples. So it's actually pretty computationally efficient because what you can do is run whatever algorithm you define that specifies a property once at a given iteration of BO on a set of function samples. And then using this, you could quickly do optimization to figure out where's the most informative point to query to get most information about the algorithm output. And this has a similar structure to information-based Bayesian optimization, how they do it in practice to compute the acquisition function there. Okay, so with the last few minutes here before we go into questions, I just want to describe a few applications of BAX that we've been working on in practice. We've actually, so this paper originally was in ICML last year. And since then, we've been really trying to flesh it out to apply it to different applications. We've been working on places in both the sciences primarily, but a little bit of machine learning applications, ML systems. There's been some other groups that have also kind of extended this to some auto ML stuff, which is pretty cool. I just wanted to describe it sort of a high level view. So yeah, the three main applications that I want to talk about. The first one is in what's called emittance tuning in particle accelerators. So particle accelerators are big machines. The one that's associated with Stanford is called from a lab called SLAC National Lab, and they've got like a 2-mile long particle accelerator. And you really care about certain properties of the accelerator to get good performance when you use it downstream in imaging applications and other type of applications to study physical properties of particles. You care about something called emittance. And usually you need to tune, either there's operators who tune it by hand, or they've tried to explore automated tuning procedures for emittance and particle accelerators. But we actually, based on looking at a slightly different optimization setting, are able to reduce the time of automated tuning and get better performance than expert operators Second of all, we've been using this in model-based reinforcement learning. So here we essentially view a property of an unknown dynamics function. You have an environment with an unknown transition function, and you can view the process of estimating optimal trajectories from a given start state or from a distribution of start states as estimating a property of a black box function. We use this for defining optimal exploration in RL. And then finally, in explainable hyperparameter optimization, this is actually by a different group from University of Hanover and University of Munich, tried to do both hyperparameter optimization with Bayesian optimization. But if you don't just want to do optimization, you actually want to estimate some information about the marginal effects of hyperparameters. So get some information that tells you for a single dimension of the hyperparameter space, if you marginalize over the other hyperparameters, so you can see what is the importance of this single hyperparameter if you were to vary it. How do you estimate this quantity while also doing optimization at the same time? And you can define a BAX setting for this task. So just high level slide each of these things. For the particle accelerators, we run it in a setting called multi-point query setting, just based on how each query is set up in these particle accelerators for querying the emittance. You actually do this scan over an alternative space, so you can define a much more sample efficient BAX method rather than Bayesian optimization. We've actually run this live at two different particle accelerators at SLAC. So one's called the LCLS, the other one's called Facet2. We're able to get something like 24% lower emittance than hand tuning by the current operators in practice, as well as something like 20 times faster than Bayesian optimization for automated tuning. Second project I mentioned is, how do we do sort of more optimal exploration in model-based reinforcement learning using this technique? What we do here is we're essentially developing either depending on the RL setting we're working with, we're making a plan to take actions that are expected to gain information about an optimal trajectory from a given point or from a given set of start states. So this enables doing efficient exploration in RL. We've got a couple of papers on this from this year. So one in iClear and one in NeurIPS that basically do this in two different settings of RL. And then finally, this paper by the group from Germany on explainable hyperparameter optimization. They're essentially doing, as I mentioned, simultaneous Bayesian optimization while also estimating these marginal effects. So if you marginalize out other hyperparameters while focusing on individual ones, can you estimate this quantity to essentially give you the importance of individual hyperparameters? Okay, so final slide here. In summary, we extended Bayesian optimization from targeting global optima to targeting other function properties that are defined with an associated algorithm. This is the task of BAX, as we've called it, and we've got a acquisition function based on information theory for this called InfoBAX, and we've been applying it to some applications in science and machine learning. If you want to know more, please check out this BAX website. I think this gives a more sort of intuitive overview and also links to the code and things like this, as well as the paper. And in the future, we're hoping to really kind of make a good systems implementation of this so we can extend this out to a broader set of experimentation tasks. And thank you for listening. Cool. So I guess we've got 1 minute left, so maybe a couple questions, or we should maybe start setup of Jiting.
I think it would be best to hold the discussion for the next coffee break that's coming up.
Sounds good.
And we should check if our speaker Jiting is online and ready to be connected.
Can you see the screen? Okay, great.
We can see it here. Can you hear us?
Yeah, I can hear you.
Okay. Just a quick introduction. So Jiting's been I guess a member of the CASL project really the longest, because he, along with some others, worked on the development of TexR at the start, and currently professor at UCSD, working on a lot of interesting stuff towards standardizing a broad set of machine learning methods. Okay, Jiting, take it away.
Okay, thanks, Willie. Hey, everyone. Yeah, it's too bad I cannot join the workshop in person, but yeah, I'm happy to discuss our recent works about a standard model of machine learning and how we can use the standard model theory to mechanically design approaches or solutions to a lot of novel fundamental learning problems and applications. So we know that we are really expecting machine learning and AI to do a lot of things right? Like the autonomous driving, machine translation, the chatbots, right? And a lot of applications in healthcare and a lot of domains. So all these different tasks and problems come with different data or experience. For example, you have a lot of data examples for maybe image classification. You have knowledge or symbolic rules for some like medical problems, right? And you have knowledge graph. You can interact with the environment and get the feedback, right, as the rewards. And you may learn. You may interact with other agents or even adversaries in some online learning setting, right? And in practice, usually you're presented with a combination of all this information, right, for a particular problem. So the problem of learning or machine learning is to make use of this experience to learn the concept or skills you really need, right, to solve the problem. Right. So speaking of learning, we know that human learning has the hallmark of using all these different type of experience or information to learn anything we want, right? For example, to learn a language, we can read examples, right? We can learn from the grammar, right? We can interact with our teacher and make mistakes and get correction from our teacher, right? And we also interact with our peers to get the feedback and information, right? So human learning can, with this single brain, we can use all these different type of information. But when it comes to machine learning, right, it turns out to be very difficult for the machine to make use of all these different type of experience. In contrast, what we get is from the decades of machine learning research is this kind of a very bewildering set of machine learning algorithms, right? Each of the algorithms was designed to use one particular type of information or experience, right? Like a maximum likelihood estimation is to use the data examples, right? Reinforcement learning or imitation learning is to use the reward functions from the environment, right? And there are a lot of other algorithms to use other type of experience. So this situation is kind of like the physics in the 19th century, right? At that point in physics, there are so many different theories to explain the phenomena in the world, right? Like electricity, magnetism, and the theory of light beams, right? But how physics really developed, right? A very important feature of physics is that the most important progress is made not by inventing new theories, right? It's really by unifying existing theories to get a more standardized one, right? For example, starting from the diverse electromagnetic theories, Maxwell defined this Maxwell's equation, right? It captures the relations between electricity and magnetism. And then this equation is further simplified with by introducing more and more unification and symmetries, right? And later, people developed a standard model that unified three of the fundamental forces in the universe, right? And the ultimate goal of physics research is to really build the theory of everything, right? To unify all the fundamental forces. All right, so that's how physics really developed. So if we come back to machine learning, right, then we would naturally want to ask, right, can we develop a standard model of machine learning, right? So let's this standard model characterize the learning using all these different type of experience, like data examples, knowledge constraints, whatever other models, rewards, adversaries, auxiliary models, right? Using all these different type of experience to learn any type of model you want, right, for your problem. Like maybe the model is a graphical model, maybe it's a neural network of arbitrary architectures, right? Or maybe it's a a world model to simulate the physical world, right? And many other different type of models, right? What's the learning mechanism in between, right? To bridge the experience and the model of and the target model. So this is our recent work discussing a possible standard model of machine learning. It turns out that we can somehow characterize many of the learning mechanisms with this single, very concise objective function. This objective function has three terms. First, so in this, you have this target model, right? P-fit. You want to learn this target model, right? It can be of any type. And you have this different experience. This experience is captured in one of the terms in the standard model. This F function captures any experience you have, like data examples, logical rules, knowledge graph. Okay. And the second term, divergence, measures the fitness of your target model in the learning system. So basically, you want to minimize the divergence between the target model and a so-called teacher model, Q, which is kind of an auxiliary distribution we introduced into the objective function, so that you found this one, and later we'll show that this equation is really a general equation that recovers many of the learning algorithms. Okay, and the third term is the uncertainty term that's characterize the complexity of the whole learning system. So you want to regularize the complexity. Okay, so with these three terms, you have this standard equation of the learning objective. So here's the illustration of the mechanism, right? You have the target model of any type. So you introduce the teacher model, which is defined by the experience you have and regularized by uncertainty, right? And then you want to measure the divergence between the target model, which is can be seen as a student, and you basically want to mimic the prediction behavior of the teacher. Okay, you have different forms of the divergence to capture the distance. Okay, so with this standard model, we show that this model really encompasses a lot of well-known machine learning algorithms in different machine learning paradigms as a special cases. So this is a subset of algorithms. We show that are special cases, like in or different algorithms in supervised learning, right? You have data augmentation, data weighting, and maybe active learning, right? And the posterior regularization, which to use the constraint in the learning process, right? And the reinforcement learning, knowledge distillation is to use another model to train the model of interest, right? And adversarial learning, and even learning in the online setting, right? We have the very well-known multiplicative algorithm, right, in online learning. So all these different prominent instances in different learning paradigms are special cases of the standard model. I won't dive into the details, but this table basically summarizes some of the relations of the algorithms, right? So by specifying the key components in the standard model, like the experience function and some alpha and beta, which are the hyperparameters in the equation, you can recover all these specific algorithms. So with this standard model as a base theory, right, what we can get besides the understanding of all these different relations between algorithms, another very practical implication is that now we are enabled to make this mechanical design of learning approaches with all experiences. Where you have all this experience in your problem, we can now use all of them to train the model of interest. So here are some examples from our recent work. The first is, okay, now we can use the symbolic knowledge to learn neural networks, right? This is an important problem in neural symbolic learning. You have a lot of knowledge bases, right? Or maybe a knowledge base in a particular domain. Okay, we can consume them as the experience function, and then you plug in the model of interest, like a bird model here, right? And then with this objective, you optimize the model, right, to consume all the knowledge information in the knowledge. Okay. And the second example is that with the flexibility of the objective function, right, you can do the other way around. You can specify the experience as a pre-trained model, and then the target model as, for example, a knowledge graph you want to learn, right? So this is a problem of learning knowledge graph from pre-trained, for example, language models. Okay, this is one of our very recent work. Here are some examples we learned out of a robotic pre-trained model, right? These are the kind of novel knowledge that which is not included in any of the existing knowledge graph, like a ConceptNet or Wikipedia, right? So, for example, you can learn the knowledge a newborn can do something, but it's not good at it, right? For example, a newborn can sit, but it's not good at sitting, right? And maybe some countries separated by ocean, right? There's even the novel relations you want. So by the way, we're working together with MBZUAI to build a knowledge server based on this work, so that users can query whatever knowledge they want from the language models like GPT-3 or OPT large models, right? So we no longer, perhaps at some point, we no longer need this human crafted knowledge graphs like ConceptNet. Okay, so here are some quantitative results. With the standard model, you basically get much better precision and recall compared to existing algorithms, like based on data mining pipelines or other kind of ad hoc design. Third example is the learning a prompt to control large pre-trained models. So for people who are familiar with the pre-trained models, right, like GPT-3, we know that prompting is a very important way to interact or to use the pre-trained language models or other models to do whatever downstream tasks you care about, right? So then the question is, how can we automatically learn the optimal prompts for your task of interest, right? So naturally, you can formulate this as a problem under the standard equation, right? Basically, you can set the target model as the prompt, right? These couple tokens in the prompt is something you want to learn, right? It's captured by fit, and then you have whatever information you have in the as the training signal, right? Maybe you have a couple of data points, maybe you have the reward function, right, or other whatever knowledge you have. Then you just plug these experiences into this experience turn, and you do optimization. So you got the prompt, right? So this is another work using kind of reinforcement learning, or like as a special case of the standard equation. Okay, so as a quick summary, we hope to build a standard model of machine learning to encompass many of the learning algorithms we already know, and also to present a design space of new algorithms we need in the real problems. And with this standard model, we enable panoramic learning with all experiences, just like how human brains can do. Okay, we show examples of new symbolic learning or learning prompts, and some other ongoing works, including building world models to simulate the physical world, like how the objects are changing, right, given actions or interactions. Yeah, so this is basically a quick overview of some of our recent work. I'm happy to take a couple of questions.
Hey, so Ziting, by the way, can you hear me as I ask a question, Ziting?
Yeah, I can hear you.
Hey guys, so it's Chirag over here. I was a little curious actually about the RL prompt, because if I'm not mistaken, is Doug your student, by the way?
Sorry, can I repeat your question?
Okay, so let me try to move a little closer to the microphone so folks can hear my question. Okay, so I wanted to ask actually from a CASL like open source perspective, this RL prompt, do you see that as being maybe integrated with certain CASL projects? For example, maybe it's the Alpha project, or is it using the Texar project? Do you have any perspective on that?
Yeah, so yeah, I do think it's very promising and potentially useful to incorporate the RL prompts as an automated way to run the prompt with the CASL project. Like say, with our Alpha, right? We serve the large language models or other multimodal models. Then how we can make best use of them, right? Hopefully we can run the prompt automatically. Right, so yeah, I definitely think this is a very useful thing, and actually compared with other, human engineered prompts, we show that our prompt is much better in terms of the performance, and also is efficient. And there are even other interesting applications, like say we want to use large model like OPT 175 billion model or GPT-3 model, which is very expensive to optimize. We want to tune it to downstream tasks, right? So IO prompt enables you to run the prompts with a smaller model, and then you can transfer the prompt to a larger model. So these are all the different possible usage of this run the prompts in practice. So yeah, I do think we are actually starting this discussion, like how we can incorporate this IR prompt within as a kind of one of the services in CASL actually. Yeah.
Great answer. Thank you so much, Ting.
Professor Marco Canini from CAUS and the leader of Sense Lab. So I think Marco is bringing us today how to accelerate deep learning via controlled, compress and manage communications.
So thanks a lot. You guys can hear me fine, right? Over the internet. This is not easy.
I think you're good to go. The microphones are connected and should be recording just fine.
Okay. Okay, so thanks again for this kind of invitation. It's great to be here at this CASL workshop. So I'm going to tell you a little bit about the work that we've been doing over the past few years on accelerating deep learning, which I think it's not one of the CASL projects, but maybe it could be, maybe some opportunities for integration. So let me get started by saying, how much I actually enjoy living in certain times, because we really live in a virtuous cycle where great data scientists, great students and whatnot can create increasingly larger models thanks to increasingly larger data sets, and this is just happening as we continue. But one thing that is happening under the surface is that all this great innovation is being enabled by costly infrastructure that keeps on also growing and evolving. We train a lot of these models nowadays thanks to hundreds of machines equipped with many accelerators, GPUs, DPUs, and whatnot. And yet, the compute requirements for some of these workloads are doubling at impressive rates. OpenAI had recently told us that they see the computer requirements for some of the largest models doubling every 3 months. And so I'll be probably not so surprising in saying, training these kind of models can still be very time consuming, whether that is in days or weeks, energy consuming, and ultimately cost. So of course, to make machine learning more efficient, we want to scale. We want to help scale. There's a lot of interest in that. It's probably $1 billion, not more problem worth tackling. And so as we grow with scale, we want to, in spirit, we want to make very efficient use of multiple resources so that we can train using massively parallel amounts of resources, of GPUs, over multiple worker nodes, large models. But this unfortunately incurs significant overheads that are due to network communication that happens. So here is some measurements that we've done in our work, where as a percentage of the total iteration time, we show how much of the time is being spent over network communication in 2 different settings at 100 gigabit or 10 gigabit per second for various models. And on the left-hand side, we're showing models that tend to be larger and also more recent, where you can clearly see that even going from 10 to 100 gigabit network may not really be sufficient to remove these operates. So the work that we've been doing is essentially trying to answer this question. While AI workloads remain primarily compute intensive, since they are not really scaling well due to communication costs, can the network be the next kind of accelerator for scaling machine learning? And I'll be focusing on the most common form of parallelizing DNN training, which is data parallel settings, in which you essentially parallelize the model. You create a replica of the model at a worker, you split the data samples, and you go compute over mini batches locally at steps, making steps of SGD or some other optimizer. But at the end of the day, you have partial gradients computed that you need to synchronize. And that synchronization entails form of all-to-all, very intensive communication pattern where data that is in the same volume as with the model, so hundreds of megabytes, if not gigabytes, need to be synchronized. So if we take a closer look at what happens during synchronizations of this gradient data, we determined that distributed machine learning really scales poorly due to this communication cost. And from the infrastructure perspective, we have all this data just traversing the network, and the network is really oblivious to that. Whether you're using standard solutions such as reduced collective communication or distributed parameter servers, the network is still really not helping you. So we're asking, is there something that the network, the infrastructure really could help with regard to this problem? And we leverage essentially some recent trends in the networking industry that led to the development of programmable data planes. So what I'm showing here is a hardware box in which there is a programmable switch chip known as Tofino. Initially was the company called Barefoot, now it's Intel Tofino, that can process 6.5 terabits of packets of network traffic per second using multiple ports. At that time, it was 100 gigabit line rate processing. Now we have scaled up to 400 gigabit, for example. So based on that technological trend, we created the system we call SwitchML, in which we co-design machine learning, distributed machine learning, with the networking supports that it needs to be very efficient at scale. Now, programming this kind of devices can entail several challenges. First and foremost, because you can only really map a limited amount of computation, and you don't really have storage on the devices. You can have hundreds of kilobytes of data, so you cannot store gradient data or model parameters as if you were to implement a very fast parameter server. Also, there is no floating points, which is the backbone for SGD. And since this is a networking problem, inevitably you have to deal with packet loss. So our design, therefore, is a co-design. So we really try to combine advantages that come from the switch machine architecture together with the leveraging host-based capabilities for any kind of processes that could not really be offloaded efficiently into the data plane. And we design a streaming aggregation protocol that is pool-based. I'll show you in a second what that entails. We also work with quantized integer operations to define the lack of floating point support, although we have done some more follow-up work trying to also support floating points directly. And we designed our own failure recovery protocol around a custom-made implementation of RDMA, because at the end of the day, what you want is to aggregate the data and send it to the GPUs as quickly as possible. This is a project that was also done in collaboration with the Microsoft designers and engineers at Intel and at the University of Washington. So I'll tell you about the streaming aggregation protocol we designed with this kind of like simplified illustration. Suppose that your machine learning job has 2 workers, and what you see here in shades of reds and blues are your partial gradients that you need to aggregate. So we view the switch as a pool of aggregator slots where we stream data using some kind of deterministic way of splitting up the gradient data and mapping them into those slots in such a way that every worker is streaming, is coupling in the streaming. And whenever the switch notices that one particular aggregation slot is full, it broadcasts back to the workers a copy of those aggregated gradients. And implicitly, that serves as a signal that now the worker, there exists an empty slot inside the switch, and the worker can send the corresponding chunk for that slot that has been aggregated. And this operation, keeps on going with this tight coupling of the communication until we have exhausted all of the data that we need to aggregate. And the advantage of this kind of architecture as compared to doing something like overduce, which is peer-to-peer based, or even a parameter server, is that we really afford the workers to use the entire line rate, the entire bandwidth on the network, and we have very low latency for doing the synchronization.
So just some clarification.
Yes.
So the actual addition of gradients happens on the switch itself.
The actual aggregation, which is an addition, yes, is an integer addition, and it happens on the switch itself.
Got it. That's why you mentioned the limitation about
Yes.
floating point.
Yes.
So I'd be interested to hear how you overcame that limitation.
Yes, that's a very valid observation. So in order to overcome that limitation, because we can only do fixed point integer aggregation, we perform integer-based quantization by adopting a per gradient chunk scaling factor that is computed by finding the maximum across all the different related blocks or chunks of gradients ahead of time. So at step n-1, I can determine essentially for a block, this is the max value that I would have for the gradients in block n. I can compute that across the network using the switch, and I can determine a scaling factor. And on the basis of that scaling factor, I essentially try to maximize the dynamic representation for converting from floating points, say 32-bit floating points into 32-bit integers. So this turns out that can work well with machine learning because there is enough stochastic robustness to it that small errors will not really affect convergence. And in addition to that, many values of the gradients really tend to be small. So with a sufficiently large scaling factor, 32-bit integers are sufficient. In practice, empirically, we observe that indeed this works quite well. This is a ResNet example. We have several more examples in the paper in which we show that by training with switch amount, one can converge in a similar number of steps to a test accuracy that compared to the original unquantized network.
And if I might just ask another question in the middle of the talk. So you said it was, I heard the words 32-bit integer quantization.
Yes.
So you're going from a 32-bit floating point to a 32-bit integer. So, obviously from an information theoretic perspective, there's an opportunity to lose nothing there because it's still 32-bit information. But I'm curious what is actually lost in that conversion from a 32-bit FP to a 32-bit integer.
In a lot of cases, the error really could be very, very small. And the reason is that a chunk here is basically a packet worth of information. So it's essentially 1,024 gradient values that we aggregate at a time. So you're already trying to scale from a floating points to, say 1,000 gradient values. You may be in a situation where your scaling factor is a value, which is a floating point value that is sufficient that you could represent all of the dynamic range of those particular 1,000 gradient values. In the worst case, you may have an error, right? So that could be akin a little bit to gradient compression. I will touch upon that, but there can be an error in representations, no doubt. Now, since we're doing this for speed, I'd just like to convince you that this is actually worth doing. And so here I'm illustrating a speed up as compared to the NVIDIA Nickel reduce library at 100 gigabit per second, where we can see that for various models there can be a speed up as HML up to 2.27x for particularly very large model deep line, which is the couple of gigabytes and has a lot of exposed communication. That is, there's a lot of communication that is not overlapped with computation. And of course, this kind of ratio, the speed up changes depending on the computation ratio. Now, these were experiments executed on a fast network, but with relatively old GPUs, the ones in orange, which were P100s. So as a thought experiment, we thought, what if we had a 10x faster GPU, which would correspond easily to an A100 and H100 these days. And so we saw that essentially the speed up would also increase for other models such as VGG and in general for all the other models that you see on the left. There is a faster speed up. The second nice property of this design of SwitchML as compared to something like Ringo Reduce is essentially that the scalability is much better because performance ends up not depending on the number of workers. And so in this plot, I'm showing the throughput in terms of aggregations, millions of elements, of gradient elements aggregated, where you can see that the SwitchML throughput is very, very close to the maximum RDMA output that would essentially be the bandwidth of your RDMA transfer, as opposed to Nickel, which suffers theoretically a 2x factor plus some overheads. But then also in terms of scalability, as you increase the number of workers going from 4 to 8 to 16, it also lowers its performance because its latency component depends on the number of workers. So it looks out. So switching gears a little bit, but still, on this train of thought, we started investigating a little bit deeper about this gradient data that we're now aggregating over the network. And we noticed that for a lot of the models that have large embedding layers, like the CTR prediction models, the language model, they tend to have a lot of sparsity, meaning that a lot of the individual coordinates of the gradients could be 0 or very, very close to 0 values. So we asked the question, how can we efficiently aggregate these sparse gradients? It would not make sense to really optimize with SwitchML while sending a lot of zeros over network. So we extended the protocol of SwitchML into another system we call OmniReduce that does sparse streaming aggregation. That is the input we assume to have sufficiently high sparsity. And then we split the data into different blocks as we did for SwitchML. But we had some metadata that essentially tells us from the point of view of each worker, this will be the next block index that contains non-zero data. And the idea is that we want to skip over all the 0 blocks. So in order to do that, our aggregator essentially has a little bit richer logic than SwitchML switch, and it maintains a global next block. So it maintains enough metadata that it can tell to every worker, this is the time that you actually need to send your block, and this is otherwise the time at which you only are on the receiving side. And this is a single thread of computation. We parallelize this over many different threads to saturate essentially the network bandwidth. The advantage of this is that we are further able to accelerate SwitchML. So this is a speed up plot where the baseline is SwitchML itself, and OmniReduce could speed up SwitchML up to 2.23x faster on a 100 gigabit network. I should have it that this was a software-based implementation of SwitchML, the protocol that I showed before, for fair comparison, since we started building OmniReduce in software, we were not really sure about the capabilities of the switch, but in the end, we also made it work on the switch itself. So the blue bars is the speed up of OmniReduce. The orange bars instead is what you would get if you were to just take PyTorch and use their default ORGather-based sparse ORReduce methods today, which is definitely not comparable. We also had quite some success with OmniReduce in that there's a Chinese company, Day-1, that adopted it for some of their workloads. Okay, so now I'm gonna really switch gears. I'm gonna tell you about some other work in which we actually take a completely orthogonal approach that says, well, if you want to speed up distributed deep learning, instead of just aggregating data really fast, you could reduce the volume of data that you send over the network. There's two main families of techniques, either quantization, where you reduce the bit width in terms of presentation, or sparsification, where you try to sample and send only just a few elements. And this actually raises an interesting trade-off, because it's no longer really just the efficiency of transmission, but you're trading off accuracy versus timing throughput, and also, in a sense, the compression and decompression efficiency, which is an element that largely has been ignored by the literature. So in order to really understand how practical gradient compression could be, we created a framework, we call it GRACE, in which we created the implementation of 16 different compressor methods, and we surveyed them, and we ran it on several different benchmarks. The finding may not really be surprising. We found that essentially there is no one-size-fits-all solution that, just tell you this compression method is best overall. And the other one is that the compression indeed has its own overheads, and we need to be aware of overheads in order to really gain in terms of throughput speed up when using compression. So based on that insight, we worked on a method that builds upon threshold-based classification, which has an O(n) complexity theoretically, so it's very low overhead. But the issue is, who's going to tell you the threshold? Estimating the threshold is actually very hard, and this paper that we had in MSIS last year uses sparsity-inducing distribution and multi-stage estimation to try to quickly come up with a decent threshold enough so that your threshold-based classification can work and very fast. And we also consider the settings in which bandwidth could actually be an element that changes, so that we can couple together adaptive compression on the basis of availability bandwidth. So I'm almost running out of time, but I really have only a few slides left. So I'll tell you that we also have a little bit more theoretical work on this in terms of how to rethink the specification from a total error minimization point of view. And we've also done work with Sam, who's here in the room, on a compression method for natural compression that is kind of helpful to work directly with the IEEE floating point formats. In the interest of time, I'll take questions on this later. So I'd just like to conclude on, since this is a workshop, something that is still brewing. So in reality, when you consider a lot of the literature with gradient compression, it's as though every worker node is actually one single GPU. But in the real data centers, you already have multi-GPU workers, and their architecture is something like this. You have a high-speed interconnect, something like MBZUAI or similar. And then you may even have a lot of NICs in order to have deliver a lot of bandwidth to the node. But everybody is kind of like thinking, if I'm going to do compression, I'm going to do either compression first locally across all the GPUs, and then, I'm going to do the reduction across all the GPUs and the compression, and I'm going to send everything over the network. Or there could be other solutions, such as compressing first and doing local reductions, and then making another kind of compression before sending over the network. So this is the topic that we're working on these days. We're even thinking, if I'm going to do something like that, and I end up with gradients that are compressed, then, why would I want to send that data over a slow PCI Express bus? Why can't I just put a NIC directly on the interconnect, maybe some kind of FPGA that can directly, where I can directly offload the cost of compression? Why should I do that? Okay, so let me conclude.
I think, yes, it would be great to do the questions, David. Right? I actually have some questions for you about the actual hardware involved here. But in the interest of keeping the schedule moving on time, Hector, would you like to introduce our next speaker?
This is Jay from National Taiwan University. So it's my pleasure to be here to give a short talk in this workshop. So my title of the talk is about algorithms and the software for text classification. Well, this is a very general title. And it seems that I have lots of materials. You see the outline here. But I have the privilege of doing like a continuous talk because yesterday I gave a presentation in a university colloquium. In that talk, I actually covered the second part, but not the third one. So instead today, I'm not going to, I will focus on the third part in my slides. Therefore, the plan of my presentation will be for the first part to give you an introduction about our open source project, and then I move to the third part. That's about some issues we faced in developing our software. So now for recently, we are doing some open source project for text classification. I think most of you here are familiar with text classification. So here are some examples. Each row is a data instance. So we have labels and then a sequence of words. And the problem may be, say, binary or multi-class. That means each document is associated with exactly one label. But it can also be multi-label, which is more complicated because each document may be associated with multiple or even 0 labels. But this is actually an area we'll study. However, we find out that tools to easily and conveniently solve users' problems actually are still somewhat lacking. For example, so if you check the multi-label classification, you can find out maybe more than 10 possible evaluation criteria. So you can consider things such as accuracy-based criteria, such as micro and Day-1, or you can consider ranking-based criteria, such as precision or MBZUAI. So which one should be used? And also, for data, they may have different situations. Sometimes you don't have many labels, such as you have only like 100 labels. But for certain applications, you may have millions or billions of labels. The way to handle such problems should be different. So then the question is, can we guide users to solve their problems? This is indeed difficult. We find out that so far for multi-label classification, we don't have some kind of like definitive recipes to tell users, say, okay, under this situation, you should use this kind of approach. And under that situation, you should use some other approaches. And this is a little bit beyond what the current automated machine learning can do. I think for automated machine learning, usually we need some, like for example, in the first talk this morning, we need a black box function. But now it seems I don't really have such things. So that's the difficulty. But anyway, because of the need for doing some implementations, so a project called multi-label is an ongoing development by my group. Well, it's a simple tool with the following functionality. So we do end-to-end services from raw text until evaluation and analysis. And of course, we support common network architectures as well as conventional ones like linear classifiers. And we support easy hyperparameter selection. Then, well, of course, we try to cover both standard binary multi-class classification as well as multi-label classification. Yeah, but anyway, I have said that now we have a tool, but we don't have an automated procedure to tell people how to effectively solve their problems. Yeah, so if you have better ideas, please let me know. I'm here to ask for your help. But now let me now I want to go to talk about a specific topic that we need to solve in designing this software package. That's an issue about whether we want to do a retraining process after hyperparameter search. So what is this issue? So here I have a figure showing a typical machine learning cycle. So in order to select hyperparameters, usually we split data to training and validation. Then, using the training data, we do the model training, we get the model. Then using the validation data, we get the validation results. That's the way how we choose hyperparameters. But then the question is, then after this is done, then we identify the best hyperparameter configuration, right? So sometimes we directly use the model with the best hyperparameters for use. Yeah, that's typically what many people do. But another thing is, should we take the best hyperparameters, then also include the validation data together to get a bigger set to retrain to get a so-called the final model? Yeah, so that's the question. Because in developing that software, we find out that should we do this or should we automatically do this for users or not? So now I have this issue called to retrain or not to retrain. So in many deep learning practice, people don't include the validation data to generate the final model. But if you look at some other machine learning methods in the past, such as support vector machines or logistic integration, well, in general, people do that. So they do cross validation to select the best hyperparameters. After that, then they use the best hyperparameters then to train the whole training set to get the final model. That's the way how people do things for SVM or logistic integration. Then an apparent reason of doing that is because more information is used. Now you include the validation set. But then we ask a question, why for deep learning, people may not do such a step, and why? But in fact, in deep learning community, people have realized such an issue, and there are already some studies. Actually, some people may think that this is an old and already solved issue. If you go to check some online forums, you find out that many engineers, they still ask about whether they should do this retraining step. So we tried to do some studies. But we found out that things are actually more complicated than we thought. So now let's check the difference between, say, deep learning and some traditional models. So we know that empirical risk only approximate the true risk. Therefore, in general, you don't need to accurately do the empirical risk minimization. However, for support vector machines or logistic integration, people do that. The reason is that those are convex optimization problems. They are easier to solve. Yeah. So people check, like, say, gradient norm for stopping. So the reason is that, well, convex is easier, so training is not too time-consuming. And also, using gradient for stopping is quite convenient. So that's the situation in the past. But for deep learning, well, now you have convex optimization, and also for each training, it's so time-consuming. Therefore, early stopping is needed, and that's everybody is using right now. But how to do early stopping? Usually, this is by checking the validation performance. Right? So you have a validation set. So then you stop run. Then you run iterations until one time point. Then you find out that validation performance no longer improves. You stop. That's the way we are doing right now. Then that becomes a question, a problem. If you want to do this retraining, it's now only for the retraining. All the available data are used, but our optimization process rely on validation data to do termination. Well, then the procedure no longer works. So that's the problem. But then, of course, we can develop some possible stopping conditions, such a situation. Basically, we want to use properties of training the best model in hyperparameter search. We use such properties for our stopping conditions. So here I use an example for illustration. Suppose in hyperparameter search for the best one, my training procedure is like this. Well, I set the maximum, I mean the iteration bound to be 50. And I happen to use, say, 18 iterations. And at that time, my training loss is such a value, and my model parameter is called f star. Then I have some possible criteria. The first one, that's a very simple one. Let's just say, okay, now I include the validation set training, but I don't know how to do stopping. Therefore, I use a fixed number of iterations. So for example, now I just say, okay, I decided to run 50 iterations. And then for initialization, we'll start from stretch. And I call this fixed epochs. So this is a very simple possibility. Then the second one is to say, well, while training the best model in the search procedure, I used 18 iterations. So why not also training the same number of iterations? Therefore, for this approach, I call it optima epochs. Then I just put all data together and I train 18 iterations. Well, this idea is also simple and it seems to be reasonable. Then there's another idea. I call this a function-based idea. So the idea is that I have this training loss. That means I have fit the training data up to a certain point. But at that time, the validation error is actually high. I have a bigger validation error. Now I include validations data for training together, right? So suppose the validation error should increase. So I just try to train until the loss of the validation set matches the training loss early. So here I mentioned that this is in doing the combined training, if the loss value on the validation set matches this 0.040, then I stop. But for this one, I can do some kind of warm start instead of initialization from spreadsheet. So there's several possible ways. And here are some sample results. And here I try 3 network models. They are typical for text classification. I have CNN, I have RNN, as well as BERT. The blue one is actually using the fixed number of iterations. The green one is using the optimal number of iterations. And the red one is this function-based. Well, we still need to check the result. So of course, the horizontal line is 0. So if I have values above 0, that means this retraining is useful. Actually, for the blue one, sometimes it is worse actually. But if you look at the green and the red one, in general, they are above 0, and sometimes the improvement is significant. This is for CNN, as well as for RNN, as well as for BERT. So a quick summary about the result. So retraining seems to be beneficial for most problems, but the best strategy is now between the green and red one. Actually, here red is better, but in this place, actually green is better. So it seems that the best strategy is model dependent. Let's wrap the observation. Well, I have run out of time, so let me quickly go to the next slide about some discussion. Well, I have a couple of questions here. So for me, as a package developer, should we by default do retraining after hyperparameter search? Well, if that's the case, then which setting should we provide? And right now, I have only studied text classification. How about the other applications, say like computer vision? Their network architectures are different, where we have similar observations. I don't know yet. And then right now, we mainly have empirical evaluation. So can we have some good theory for this issue? Okay, so thank you very much.
You actually have time for questions because you are the person who actually ended on time. So we can take 3 minutes of questions if anyone has questions.
I like to be on time. Yes.
Can you go back to the results slide there?
Oh, yes.
3 strategies.
Yeah. I didn't spend enough time to.
I think this was eventually clear to me, but the assessment that you're doing here for these is on some additional test set, is that right?
Oh, yeah, right. There is an independent test set. So actually, it's very difficult to do this experiment. For every setting, I need to do complete hyperparameter search. Okay. Then after that, I do the retraining. Then I do the prediction on an independent test set. Yeah, it's very difficult to do this experiment. Yes.
And also as for the function-based one, you said you were inserted into like the optimal weights, like parameters on the whatever hyperparameter is optimal. Do you is usually the loss val less or greater than the optimal one when you initialize it on the validation set, and then it goes down and you stop it at the previous clusters?
I actually have a table here. Okay, this shows everything. This is a good example. So for the first row, this no retrain, that means the information after hyperparameter search. So you can see that the training loss is this, but validation loss is actually high. It is high. But this is a case that so we intend to reduce this validation loss to match the training loss here. And we really get that. But the problem for this example is that then somehow we overfit the training part, the training subset. So for this case, actually, the function-based approach doesn't work as well as the Optima Apex one. So the Optima Apex one, for this example, you can see the training loss as well as the validation loss. They both match the original training loss. Therefore, no overfitting happens. That's a good case for this approach. Yeah.
Also, did we see the, I'm wondering if we, I'm not familiar with the metric you used on the final results plot, but I'm just wondering if the validation set is used in a number of just standard deep learning applications. Do you expect that the metrics that you can go up significantly? Like, is this a big increase when you use your strategies there?
Oh yeah.
Like the
Okay.
metrics here, is that significant?
Yeah. So for at least for this data set, you can see 10% improvement. That's very significant. Oh yeah. You see this figure here? No, this is not. So this is actually 10%, more than 10%. So this one is significant. But for other, but another thing I didn't mention is things related to the ratio of data you use for validation. Okay, if your validation set is very small, well, then no need to do this. But you need a bigger validation set, then of course you need to include it for the final training. Okay, so thank you again.
Okay, let me make sure I'm on camera. Okay, so let me introduce you. We're very honored today to have Professor Kun Zhang, who's not only the vice chair of the machine learning department here, but he's also the director for the Center for Artificial Intelligence, which means he's my boss, because I'm from the CAI as well. And then today he'll be giving his talk on causal representation learning advances and perspective. So please take it away, Kun.
Thank you very much, Xiong. Welcome to MBZUAI. So if you need anything, please let us know. We are local hosts. So thank you very much to the organizers and especially to Xiong, Phil, Silver. Really, yeah. So welcome. Okay, so today I'm going to talk about the causal representation learning. I'm going to report some advances, and at the same time, I'm going to share some perspectives. So you can see that in this task, we care about not only CASL of the learning the system, but also the CASL property of the learner representations. Essentially, we want the learner representation to be composable, right? And scalable, and at the same time, we want to have an automatic approach with as few interventions as possible to learn those things from data. So here you can see, first of all, we really care about the causal representation or causality. If you want to do domain generalization or domain adaptation, you try to see how different scenarios are connected. And then because of connection, you can do transfer. And when we make decisions, clearly we have to give a reason, right? We have a reason. And when we make decisions, usually we want to change something, right? Clearly you care about the effect of interventions, and you want to see what part to change in order to make it effective. And when you make recommendations, the same thing will happen, right? You have to give a reason, at least you have to give the expected outcome. And similarly, when we are recommended, right, machines recommend something to us, we would like to see the results. Essentially, it's about explainability and actionability of the machine learning problem, of machine learning, of the outcome of machine learning systems. Furthermore, here you can see a very famous example to demonstrate a common problem in deep learning systems. We have essentially the adversarial vulnerability problem, right? It's panda, but after you add some noise of a particular pattern, or if you change some pixel, all of a sudden machines say, oh, it's something different. Why? Why could it happen? How can we really avoid this problem? So we have some recent papers on it. Basically, you can mathematically show the following thing. As long as machines and human beings actually learn and make use of different sets of high-level representations of the features, then this is always the case, because you can always tune the input, raw input, so that either machines or human beings, right, will say something different. That means in order to make sure machines and human beings can really communicate with each other seamlessly, what can we do? We have to understand what kind of feature representation we learn and make use of. And we have to equip machines with the same ability, right? To learn features consistent with what we use. Then next question is, what kind of features do we use? Here, let me just say a few words about causality. From data, we know dependence. You can use the joint distribution, conditional distribution, or some other measures, right, to describe how they are related. But when we say causality, it's more informative. Here, X and Y may have the same dependent pattern, but the causal relation can be totally different, right? If X causes Y, as you can see from here, you cannot see it. So if X causes Y right here, you can see intervention on X will change Y. But in the two alternative models, even if they are correlated or dependent in the same way, intervention on X will not change Y. So clearly causality will be more informative, and we want to understand how. Now, next question is, why do we need causal representations, right? Let's try to give a more fundamental answer. Some people say, with the causal representations, we can really benefit some downstream tasks. Yeah, that's the case, right? We have a lot of evidence, but still we need to provide evidence. And sometimes we say, yes, we care about the why questions. So this provides a way to answer such questions. That's good, right? And furthermore, some people may say, actually, we are trying to recover the property of the true process. That might be the case, but the true process could be very complex. Here, I would like to give a further philosophical argument. So basically, this is the world of experience. I can stand here, right? So this is the world of experience. This is basically the world we can perceive. And right here, according to Kant, this is the Kant's metaphysics. So this is our world, and that's the world in itself. But we can never directly perceive anything of world in itself. We can only have, we can only perceive this guy, this world, and whenever we see something here, we already applied some forms of experience. Basically, it's like a filter. So this filter system consists of concepts of space, time, causal order, and so on. So that means that whenever we try to analyze something, we already have the information of causality right there, and time information, space information, and so on, right? Given that, we would like machines to have the same ability. The machines can automatically apply causal understanding, the concept of time, and so on to the data and discover consistent representations. Okay, so we care about the representations. And furthermore, how can we make it possible? We have only observational data. How can we really recover causal information from data? To answer this question, we have to address two issues. First, what kind of information in the data actually can reflect causal information? In other words, what kind of footprint can we find in data? Footprint of causality can we find in data? So I'll talk about that. The second question is, given the constraint or given the property of the data, can we recover the underlying causal model or structure uniquely? This is about identifiability. It's the identifiability of the underlying causal structure from data. So the answer to the first question is essentially known as the modularity property of a causal system. So here we are talking about composable representation, the composable learning process. This is the modular representation. They are somehow related. By modularity, I mean the following thing. We have a causal system right here. Even if all those variables, including rain, wet ground, slippery, are dependent, actually we have separate, irrelevant modules. Those modules are not related to each other. One module generates rain. The second module generates wet ground from rain. The third one generates slippery from wet ground, and so on. So those modules do not share parameters. They are completely irrelevant. We can change one without changing any other. If they change independently, right? So this is modularity property. Essentially, this is the most fundamental property of a causal system. We view this world in a very simple way because of causality, right? We can automatically decompose very complex systems into a lot of simpler modules, and then we can put different modules together to establish some big system. Okay, this property, modularity property, immediately gives rise to three properties that we can see in the data. First one is the conditional independent relations in the variables. The second one is the independent noise condition. Basically, the noise would be independent from the cause if there are no latent confounder. The last one is the minimal and independent changing property. So basically, if you see changes in non-stationary environments or heterogeneous environment, then the changes would be minimal and independent. right? So this is because right here, those modules are not related. If you have change here, with the wrong representation, you are going to suffer more changes, and the changes will be dependent. Okay. The second thing is how to establish identifiability. So all those approaches or developments I'm going to report have identifiability guarantees. By that I mean the following thing: under the appropriate assumptions, you can show that the learned representation, like call structure, latent variable, and their relations, will be consistent with the underlying truth that you assumed, right? Okay. Now let's consider the problem, the three axes of the problem. First, what kind of data do we have? Do we have ID data as input, or do we have heterogeneous or non-stationary data or temporal data as input? So this is the first dimension. The second one is whether we can benefit from some parametric constraints, like linearity constraints, right? In some cases, if you know a system is almost linear, then the problem can be simpler. The last one is whether we allow latent confounders. Of course, in this world, we have latent confounder almost everywhere, right? So practical methods usually can deal with the latent confounders. Now let's see how we can do. This is the basic summary of the recent advances in the field. So you can see for each setting, right? Basically each combination of the three axes. Then on the right, you can see what we can get. So in the ID case, basically the problem is very hard. We have only a single distribution. So usually we can end up with some equivalence class. And if you are willing to make some further assumptions about the causal influence, then in some situations you can recover the underlying truth uniquely. But basically, in a non-ID situation, the problem will be simpler. Okay, you will see why. So here, let me start with an example. So this is the data set collected by my collaborator, Marlin Novak. So in archaeology, they really want to see why people in different areas look different, right? They collected 250 skeletons. They try to see the reasons of the difference. So the features including sex, cranial size, diet, location, climate, and so on. So in this case, clearly we cannot really do intervention. We have to analyze the data, and the relations can be very, very nonlinear. We have no idea. Some features could be very high dimensional, like the cranial shape differentiation, right? It's 255 dimensional. Here we just apply the PC algorithm developed by Peter Spertit and Clark Glimmer, PC, combined with the kernel-based conditional test. Now we can see we only make use of a conditional independent relation in the data, but you can get something very informative, right? From the data set window or gel distance, it causes the climate causes cranial size, you can see gender causes cranial size, and so on. So by only in conditional independence, you can already find something in the data. Of course, here we assume there are no latent compounder, so you want to go further. And furthermore, with the conditional independence, sometimes we cannot find the direction. If you have only two variables, right, you can only say whether they are independent or dependent. You cannot find the direction. But if you make some rather mild assumptions about the causal mechanism, all of a sudden, cause and effect are not symmetric anymore. You can really figure out which one is the cause and which one is the effect. In the linear non-Gaussian case, as you can see from here, from cause to the effect, right, you can find the independent error, but from effect Y to cause, you can never find an independent error, although the residual is always uncorrelated from the predictor by construction of linear regression. So you can see asymmetry. In the wrong direction, you cannot find an independent residual. The same thing happens even if you have very flexible model, post-nonlinear model, or kind of a special case, additive knot model. So here, this is a measure, is a way to measure sensor measurement distortion. It's very important, this function in practice, because very often times we have a lot of distortions. But basically, we can find the causality from data if you assume there are no latent compounder. Okay, so that's the first part. We developed the so-called causal learning package. I talked to you about it. So this package contains implementations of almost all those state-of-the-art causal discovery methods that are proven to be kind of somehow reliable. And in most of them, we don't really deal with the latent compounders. So that's a second part of the talk. And we try to use composable implementations. Essentially, as you can see from here, we analyze all those methods. We try to see which modules are shared and which, right? And then we have a hierarchical way to organize all those modules. So in this way, you can see users can easily make use of some functions and implement their method. And basically, the package is easily extendable and refinable. So this is how we implement the package. I would like to get some suggestions from you because you guys are professional in this particular field. Now, you can see we try to analyze the relations, right, of among different methods, and we find the algorithms and the modules and so on. And finally, we have a very, very nice way to organize all those modules. Okay, now let's go to a kind of more difficult situation. How can we recover the latent confounders and their relations? So here, this is the motivating example. We have answer scores in psychometric studies, right? We have questionnaires, then we can collect answer scores. From the answer score, what can you get, or what would you like to get? We want to get the underlying mental conditions, right? The answer scores are not directly causally related, although they are dependent. It's just like image pixels. Nearby pixels are related, but they are not directly causally related. We cannot say this pixel causes another pixel, right? So we want to find the high-level latent variables and their relations. Okay, so in the last years, we developed a set of methods. Here, let me just briefly report the result on one data set, the teacher burnout data set. Here, they measured 28 variables, and they had 500 data points. So this is a model given by experts. So they don't rely on data. They just make use of their domain knowledge to produce this hypothesized model regarding how those variables are related. Here, those are kind of latent variables, and you can see latent variables are related. And with our kind of recent method, we got almost identical results. So it's cool. Basically, verify two things. First of all, the domain experts are very good because they didn't look at data, but they produced something that can be verified by data. At the same time, computational method could be very useful because you can really recover something about the domain knowledge. Okay, now we can go further. So in recent works, we try to recover the deep hierarchical structure by analyzing the measured variables. So here you can see with only xi variables as the input, you can recover the whole hierarchical structure, including latent variables and their relations. Okay. Later you can see how you want to kind of make it even better. And this is the IID case. If you go beyond the IID case, all of a sudden it's much simpler. Let me just give you some examples. So this is our result on learning underlying representation from time series data, say video data. Basically, let me just give two results on very simple data sets. So this is the kitty mask video. With this video basic pixels as the input, we immediately recover the three latent processes. Turn out that they are independent. So the first one is the movement in one direction, and second one is the movement in the orthogonal direction, and the last one is the size of the mask. In the second data set, which is known as the mask screen video, you can see here we have 5 balls in different colors, and between some pairs of balls, there are hidden springs. So with this video as input, we recover 10 latent processes. They are just XY coordinates of the 5 balls, and we also recover the location of the spring. As you can see how they are related. By making use of some causal principles, it is completely possible to learn the underlying representations, underlying concepts, and their relations in a completely unsupervised learning manner. Okay, so do I still have time? Okay, I'll finish. Oh, 5 minutes. Okay, I'll finish the screen. Thank you. So now let's go further. So I will talk about temporal data, right? IID data and temporal data like time series. Now, in many cases, we have non-stationary data or heterogeneous data. We have multiple distribution. Actually, from a causal perspective, this kind of data set is so useful. Why? Because without changing anything, we can forget about the causality. We talk about causality because we want to change it. We want to understand why and how they change. We want to apply changes, right? So in other words, causal modeling and the distribution shift are heavily coupled. If you know causal model, you know how the distribution may change. They change, right? Different modules can change. They must change independently, and so on. In the other direction, if you can see distribution shift in the data, then you can easily verify whether a particular hypothesis regarding causality holds true or not, right? You can see whether, if this model is true, here I can see some extra dependence, then you know, it's not plausible, right? So we did some work regarding how to recover causality from non-stationary or heterogeneous data. So I would say this set of methods would be more reliable in practice. Why? Because actually you rely on more information. You have more distributions, so it's more informative. let me just briefly say something about this method, which is just causal discovery from non-stationary or heterogeneous data, CD0. First of all, from data, we can figure out for which variables the causal mechanisms change over time or across different domains. So you can say, oh, for V1, the generating process changes. And the second, we can find a true causal skeleton. And then by making use of independent chaining principle, we can find the directions of causal influences. Okay. And lastly, we can also find a low-dimensional representation of the change in the causal mechanism. Why? Because the causal mechanism can be represented by the conditional distribution of the target variable given the parents. Now you just want to find a low-dimensional representation of the change of this kind of complex conditional distribution thing. We use the kernel method with embeddings. Okay, so good. Now we can do something from non-stationary data. Furthermore, in the previous one, we assumed that we only allow a specific type of confounder, latent confounders. And in this recent work, basically the message is very clear. We have non-stationary data. And then if you assume that the difference in the distribution is caused by, say, the change in very few underlying components. And if you assume that the underlying components are independent, then you can immediately achieve the following thing. First of all, for the underlying component with change in distribution, you can just recover the component without any problem. So we can recover this component or this concept up to some invertible function for each of them. So that's good. So we can recover the components. And for the invariant things, right, which have the same distribution across different distributions, different domains, then we can only recover them up to the subspace. That's completely sensible, because if there are no change right here, what can I do? I can only recover, say, function or subspace of all those concepts. In other words, whenever something changes, we can recover it. If it's always the same, then basically it's a part of background. We cannot recover it, right? So that's the message. Now, this is basically the second to last one. You just saw that causal representation learning benefits from non-stationarity and heterogeneity. That means that if you have more distributions, then it's easier for you to learn causal representations. And the current approach basically just puts all data together and then try to learn something from the whole big data set. That's not really what we do, right? We learn those things sequentially, right? So here we have this representation, but we can just generate new concepts. We learn sequentially, we can generate new concepts. We can refine our previous understanding, and we can allow a huge number of concepts on our mind. So given that, we would like to have the kind of CASL property of the learning process and the learning outcome, learning output. Basically, the learning concept should be composable and extendable. And the learning procedure should be scalable with respect to the size of the data, the dimensionality, and the model size. And we should have an automatic procedure to do so. So this is the basic. We are right now looking at this problem. We try to use the continual learning and some other way to deal with the problem. Okay, to summarize, we care about causality. A lot of problems in machine learning actually are related to causality. In the second order, with appropriate representation, we can really allow machines to do something we can trust. Essentially, the way to achieve explainable and trustworthy AI. And it is possible to learn causal representations or pseudo-causal representation. By that, I mean the following thing. In some cases, we don't have those assumptions, but you can still use the representations as a way to achieve, say, some very good properties, although they may not be the causal model. And finally, you can see that the design of the kind of tensor procedure for learning the causal world really needs a lot of efforts. So I'm looking forward to your contribution in this line of research. Thank you very much.
All right. So I guess because we are a little bit behind schedule, if you don't mind, if we can leave the discussion part to the next session, and maybe.
Okay. The next speaker we're going to hear from is Sang Cho from Carnegie Mellon, who's going to talk about some very interesting work on multi-level optimization.
Thanks for the introduction. And my name is Sang, and today I'm going to talk about systems and applications of multi-level optimization. This work is a collaborative effort with Willie, Peng Tao, and Eric. So I'm going to start the presentation by asking this question. So what is missing in current machine learning? I guess like Professor Kunze also talked about causality as one of the things that we're missing in current machine learning. But another thing that we're missing is the interactive learning scenario. So if you think about the current machine learning, if you're like given the task like image net classification or the like machine translation, what they do is basically finding the patterns in data to solve the task, and there's basically no interactions with other agents. But in human learning, as shown in the below figure, let's take a, let's consider the school interactive learning experience. Like for example, teacher gives homework to students, and then given this homework, students try to solve all the homework and update their knowledge. And then after finishing homework, students take a test. Then teacher evaluates the students' performance in the test, and if they are not performing well, they also update the homework to give a better experience for better learning experience for students. So by interacting between this teacher and students, they make this teaching and learning experience more efficient and helpful. But we're not the social science workshop, we're at the machine learning workshop, so we want to understand this from the machine learning perspective. So if we take a closer look at this scenario, so from the students' perspective, their main goal is basically solving all the homework problems. And in doing so, they also update their knowledge. And also from the teacher's perspective, their main goal is basically improving students' test score by designing a better homework. And then in this case, what teacher does is basically updating the homework. So if we approach this scenario from the machine learning perspective, these green parts, the solving homework problems and improving student test score, is kind of very similar with the optimization objective, like the loss function. And then the orange part, update knowledge and then update homework, are very similar with the parameter update stage in machine learning. So basically, teacher and students are solving the optimization problems, but the unique characteristic of this scenario is that these two optimization problems are interacting through these red and blue arrows. And now we want to kind of understand this scenario, the interaction between optimization problems, a little more formal way using some mathematics. And that's where multi-optimization comes into the play. So multi-level optimization basically refers to a problem where we want to solve the nested optimization problems or the hierarchy optimization problems with two major criteria. The first one is the lower level problems are constrained by the current solution of the upper level problems. If you consider the previous scenario, the low level corresponds to the student and then the upper level corresponds to the teacher. So the students are trying to solve the optimization problem given the homework from the teacher. And then teacher, which is upper level, the second criteria, the teacher is constrained by the optimal solutions from the students, which is the knowledge students gained after solving all the homework, and then try to improve the homework designing, constrained by the optimal solutions of the students. So if you look into the middle equation, so the blue part is basically the upper level constraint, and then the red part is basically the low level constraint. As you can see, upper level constraints are the non-optimal solutions, and then the low level problems are the optimal solutions. So in this way, we can formulate the interactive optimization problems more formally using multiple optimization framework. And there are actually multiple ways to solve this multiple optimization problem, like Bayesian optimization as really presented earlier today, and like evolutionary strategies. But in this work, we want to focus on the gradient-based multi-optimization. This is because in the current deep learning era, a lot of optimization problems are really high dimensional. And then those used are the optimization methods like Bayesian optimization, evolutionary strategies, oftentimes fail to scale to this kind of large high dimensional problem. So in gradient-based multi-optimization problem, we want to basically calculate the gradient for each level. And then this gradient can be decomposed into two parts. The first one is the direct gradient part, and then the second one is the indirect gradient part. The reason why we want to consider the indirect gradient part is because our optimization problem is constrained by the optimal solutions of the low-level problems. But then these low-level optimization, the optimal solutions from the lower level problems can be a function of the current level parameter theta k. For example, in the previous teacher-student example, student solution is constrained by the teacher's current homework theta k, theta 2. So L1 is basically a function of the theta 2, and we want to take into this account when calculating the gradient. And even though we had just 2 agents in our previous example, in real scenario, there can be actually way more complicated interactions between multiple agents, and that can be all formulated using by recursively applying the chain rule as in the below equation. So to perform the gradient-based multiple optimization, what we basically need to do is computing the below equation. And there are actually several challenges in calculating this equation. The first one is the computation complexity. We are dealing with the really high dimensional problems. And then these red and green parts, which is called best response Jacobian, can be like millions by millions if we are considering like the millions dimensional problems. So computing this million by million metrics, or even saving this millions by millions metrics is computationally and then from memory perspective really expensive. So what we notice is that the rightmost term is vector. So instead of doing the matrix multiplication, by performing matrix and vector multiplication from right to left, we can reduce the computation complexity from cubic to quadratic. And now that we are doing the matrix vector multiplication, what we basically need to do is recursively performing this matrix vector multiplication with best response Jacobian. But then here, there is another problem because now we want to differentiate through the optimization. For example, in student-teacher example, we want to differentiate the outcome of the student's knowledge with respect to the teacher's homework. And then differentiating into optimization is really not straightforward. So we normally use the technique something called like iterative differentiation or implicit differentiation. But as you guys have already noticed, I guess a lot of people haven't even heard of these terms in their life. So one of the difficulties is definitely programming mathematical proficiency in understanding what is iterative differentiation is, what is implicit differentiation is. And then another issue is that usually in this iterative differentiation or implicit differentiation, they usually calculate the second order gradient like Hessian information or the multiple forward backward propagations. That means that you're using way more compute and then the memory than the traditional training. So we also have to deal with this memory and compute bottlenecks even after understanding all the programming and mathematical details about those algorithms. So, but no one wants to do this. So that's why we decided to develop our multiple operation library, Betty. So what Betty does is basically doing all this gradient calculation automatically. And then also we also added a lot of system support like distributed training and mixed precision training to solve the memory compute bottlenecks. And then also we provide a modular programming interface for various algorithmic system design. For example, there are multiple algorithms for iterative differentiation or the implicit differentiation. We let users to choose whatever algorithm they want using just one line of code change in our library. And in doing so, we wanted to democratize multiple optimization and let users model the various interactive learning scenario in an easy way. So here's some examples of our code. So basically, so there are 2 major components in Betty. The first one is the problem class, and then the second one is the engine class. So in the problem class, we define each level's optimization problem. How do we do that? It's very similar with the PyTorch Lightning. We define the loss function, and we provide the module optimizer data loader, and then that's it. That's like how we define the optimization problem for each level. And it's very similar with PyTorch Lightning. So I guess most people won't have any problems in learning this kind of framework. And then the second one is the engine class, where so in the previous problem class, we defined the optimization problems. But in the engine class, we define the interactions between the optimization problems. And how we do it is basically using the Python dictionary. So we have upper levels and lower levels, and then there are 2 types of interactions. One is upper to lower, and then the other is lower to upper. we define these kind of interactions using Python dictionary, upper to lower and lower to upper. And we just pass these dependencies into interaction dependencies into the engine class. And then finally, user just run the engine that run, and everything will be automatically taken care of by the API Betty. Yeah, so that's the systems for multiple optimization we developed called Betty. And there are actually a lot of cool applications of multiple optimizations, like meta learning, hyperparameter optimization, neural architecture search, reinforcement learning, adversarial learning can all be formulated as multiple optimization. For example, in adversarial learning, attacker, and we have two agents, attacker and defenders, and they are interacting with each other. Reinforcement learning, we have like multiple agents and then environment interacting with each other. Hyperparameter optimization, we have hyperparameter and the main network parameter interacting with each other. We can all model these kind of things using our framework Betty. But in this presentation, we specifically want to focus on automated data preparation application. The reason why is because I guess a lot of you guys may have heard of this already before. Like 80% of the data science test time is basically spent in data collection, organization, and cleaning. And it's just not about the data scientist productivity. Also, like 75% of the data scientists report that the most boring and the least enjoyable part of their job is basically this like data cleaning, data collection, organization. So we decided to ask this question: can we automate this part by cleaning this like noisy and imbalanced data automatically? And then that's where multiple optimization comes into play. So we again borrow the teacher-student example here. So we have teacher who re-rates and collects the data, and then the students basically solve, try to learn from the noisy and imbalanced large training data, but re-rated and corrected by the teacher. And then after finished learning, students take a test on small clean validation data sets. And then if the student's performance is kind of poor on the validated data set, the teacher updates their re-rating and correct mechanism. And we just like iterate this procedure like multiple times until students really perform well on the clean validated data sets. And then after that, we can kind of say that because students is performing well on the clean validated data set, we can kind of safely say that the data is correctly cleaned. So this problem can be basically formulated as an extended bi-level optimization problem, where we have two optimization problems on the second level and then one problem on the first level. The second two problems on the upper level is basically label correction, then the data re-rating, and then the bottom level problem is like whatever problems that the data scientists have. So thanks to our library Betty, we were able to really clean. Make the program interface really simple for the users. So basically what users need to do is providing the model optimizer, optional linear scheduler, and then data loader. And then they just, again, train another run. And then it will automatically do the data cleaning by doing label correction and data aggregating. And this is the performance we get. So we first tried our algorithm into cloning 1 million data sets. This is the web crawl session data with the 1 million data points. And then the noise ratio is approximated to be like 40%, and the imbalance ratio is like 5 to 10. In addition to this large dirty data, we additionally constructed 7,000 clean small validated data set. Compared to the 1 million data points, 7,000 is even less than 1% of the whole data. And after performing the automated data cleaning by the label correction data aggregating, we observed a performance improvement of like 7% in absolute scale, maybe like 10% in the analytical scale. Just by cleaning less than 1% of the data. And then that was the image classification task, and then we also tested our model of the text classification example as well. So a lot of people these days use like weak supervision from Snowflake AI for generating training labels very quickly. But because of the nature of the weak supervisions, the labels are usually very noisy. So this is the first row basically shows the label accuracy generated by the weak supervision algorithm. Like it's like the lowest one is like 50%, and the highest one is like 84%. And then fortunately, we have the access to the gold labels for this all these data sets here. So the second row performance basically shows that the performance we get from training our model on the gold labels. So we can, this is kind of the upper minimum we can achieve with these data sets. And then the baseline performance is basically the performance we get from training our model on the noise data. And as you can see a lot of like performance degradation for all the data sets. And then the final is after applying our data cleaning algorithm. Approximately, I guess, 10%, so the validation size is about 10 times lower than the training data set for all these tasks. And just by collecting 10% of the data, we were able to recover the full performance, the gold performance for almost all tasks. So that being said, now we don't have to spend a lot of time including training data. You only need to spend like 10% or even like 1% of your time including the data, and then guide your, and using this clean and validating data set, we can guide our training by reweighting and then correcting the data. And actually we can add more strategies like data augmentation or data invitation. This is some of our future work. And yeah, so this is something that we're trying to build on like data-centric MLOps platform in the future. And another thing that's really nice about this framework is that we don't touch anything about the model and then the loss function here. But once you have like a working model for your business, people are kind of really reluctant to change their model of the loss function. But we are only dealing with the data parts here. So people would be more willing to, and you know, like a change in the data is like, you know, it happens all the time. People think that they should clean the data. So changing the data, people has no mental barrier. But like changing the model and loss function, they may have a higher barrier. So that is really nice part. And then we make this process really cheap by only allowing users to, you know, play around with the validation data set instead of the large training data. Yeah, so yeah, that is the end of my presentation. Thank you.
Maybe just to keep on a schedule, hold off on questions till the break, which is coming up.
Agreed there. I believe it's academic affairs. Did I get your title right, Tim?
Academic and student affairs, yes.
Academic and student affairs, right. And he's also, I would guess, perhaps the founding member of our natural language processing department, really a pivotal figure here at MBZUAI. And a lot, he's going to be giving his talk on AI ecosystems, the case for natural language modeling.
Thank you. Sorry, I'll just share my screen again. You can see the slides okay? Okay.
We can see it. So
you can see the slides okay?
Yeah, it's okay.
Excellent. Okay. So apologies for doing this virtually rather than in person. I come to you from South Korea in a very historic temple right near Gyeongju down in the southeast. I'm here for a conference for colleagues. So a slightly surreal atmosphere to be giving a technical talk, but bear with me. So what I wanted to do in this talk was give you a bit of an overview of natural language processing. Being mindful of the talk just now that I got the tail end of was talking about birds. So you've obviously been exposed to some of the concepts that I'm going to be presenting here. And so I'll do this in two major parts, a bit of a background on how modern day NLP works, the sorts of models that we use, how we train those models, and what the implications then are for the ecosystem, and then talk a little bit about model sharing and modern NLP paradigms and implications for open source and the broader ecosystem. So just as framing remarks, I'm not attempting in this short 15-minute talk to tell you everything there is to know about modern day NLP. It's sort of very shallow and broad with a focus on the ecosystem, no squiggles, no algorithmic details, lots of hand waviness in terms of the intuitions, but hopefully it gives you a better sense, I guess, of where NLP is actually. So natural language processing, as hopefully you're aware, is all about processing of text. So it focused on the fact that much of the archived human output, as in direct archived human output for different cultures, is in written language. And different languages have developed different writing systems. For example, the Rosetta Stone on the left here, and one of the first Japanese novels that's still in existence called The Tale of Genji on the right. Of course, there are lots of languages without writing systems, but I'm focusing on those with here. So given the central place that text has for not just communication, but archiving, particularly for more formal purposes, whether that be technical documents, as this audience is very familiar with, legal contracts, legislation, scientifically speaking, when we publish our work, it's very much in text, which is a slight oddity when you think about it, because it's such an imprecise medium in which to present such deep conceptual ideas. So NLP is all about extracting knowledge from that text or converting it into a form that's actionable, whatever that means. So as examples of that, coming back to our example of the Tale of Genji, it could be in the top right here, machine translation, say, taking the original Japanese and translating it into English, or in the bottom right, something like dependency parsing or some form of information extraction, capturing the fact that in this opening sentence of the Tale of Genji, the emperor loved a lady. So surfacing the latent semantic structure of the text. So I'm sure many of you have heard this term large language model. So nowadays, much of NLP is based on large language models for all sorts of NLP applications. I've just given you a sort of broad spectrum of different styles of NLP application here to give you a sense. So anything from sequence tagging, you can find all of the people mentioned in a given document for a service like LinkedIn, say, document classification, so document label labeling, is it spam or is it not, say, for an email provider, machine translation, as we saw in the example just now, summarization, so take a single document or multiple documents and distill them into some shorter textual summary, image captioning, so it doesn't have to be text to text or text to structured or semi-structured representation. So nowadays there's more and more at the interface with text and different modalities like images and speech, obviously, I guess. So what is a large language model? How do we train? So the two major components are representation learning, which is a fancy way to say that we're projecting words or fragments of language onto what's traditionally nowadays dense vectors. So think of that as a list of floats, or a dense vector of real numbers, depending on whether you're more computer science or mathematically inclined, also called an embedding. So people often talk about embedding learning, word embeddings or document embeddings. So that's the first part. So that's what we're trying to translate text into and from, as we'll see in a moment. The second part is what's called pre-training. And the key idea here is using what's called self-supervision. So the self there is, it's supervised, but we don't rely on any external labeling. We're deriving labels based on the raw text in the form of tasks such as what we have depicted in the bottom of this slide. Like I'm masking, as in hiding a word within a particular context, and I'm trying to get a model to predict what is the word that I have masked. So in this example, in the top example, the cat something on the obvious candidate there would be something like sat or slept or something like that, some verb. Or in the bottom example, rather than taking context and predicting a single word, we're taking a single word and predicting the contextual words around it. And this is a particular instance of a very early example, as in all of 9 years ago, but in terms of large language models, very early, called word2vec, which people may have heard of. So the more modern methods, it's harder to describe. So let me just, in the context of the sort of now very much outdated word2vec, just give you a bit of a sense of how these models are pre-trained. So in the first example, where we've got the cat, a masked word on the, and we're trying to predict what that word is, we do something like this, where the representations we have for each of our context words is an embedding, as we said before, so a vector of real numbers. We have some method of aggregating over those. In the case of the placebo model, it's a simple summation across the individual values. And then we have prediction that we're doing off the representation, the aggregated representation that we generate there, using something like a sigmoid, say, where we want to be able to predict SAT or whatever it is in this particular context. Let's assume it's a SAT with high confidence and anything else with low confidence. And so we have some learning objective which encourages that behavior. And in performing this pre-training across lots of data, we learn these representations which maximize the predictability of or recoverability of these masked words. So nowadays, very few people play around with word2vec. It's all about transformer-based models. And I'm not going to go into what a transformer is. That would take a lot longer than just the 15 minutes. But BERT we had mentioned before. So BERT, it's all of 3 years old, but it sort of, given how rapidly things are moving, it sort of feels like an old model nowadays. But a lot of the work is styled around BERT. So I'll sort of describe the very basics of BERT to give you a feel for it. So in the case of BERT, we have a similar objective in terms of the masked language model objective, except that instead of for a fixed context, such as 2 words to either side of a word, predict the masked word, I've got some variable width context, and I'm doing stochastic masking, as in I have some random variable, some hyperparameter in terms of the proportion of words and the prior for masking a given word. And across different passes of pre-training, I'm going to be predicting different masked words in the same context, with the important differentiation over word2vec, that these are going to be contextualized. In a given context, the representation that I would generate for the same token is going to be very different, whereas in the word2vec case, it's a word embedding, so I will generate a single representation, a single embedding for a given word aggregated across all of the occurrences of that. So masked language modeling is sort of the basic, the absolute sort of bread and butter of modern day large language models. And then different language models have different secondary objectives that they often combine. The original BERT had something called next sentence prediction, where you had a concatenation of 2 sentences, and the simple task is, does B follow A as a sentence? And the important thing to note here is these special tokens that we have. So we've got our first sentence and this SEP token, the second sentence with a SEP token. So we're injecting structure through the use of these special status tokens and attuning the model to the fact that we're actually, we've got in this particular case 2 sentences, and in other cases maybe we'll have more than 2 sentences. We can have other special status tokens to represent different structures. So that's sort of the very basics, and BERT is an example of something called an encoder model. So through this pre-training, largely based on masked language modeling, what we're doing is taking different contexts and generating representations. And in practice, we're generating individual contextual representations for each of the tokens, as well as an overall representation, which is canonically associated with this special CLS token that as the starting token. But it's an encoder in the sense that we take text and we generate these embeddings for the text, for individual tokens as well as overall. We also have 2 other key flavors of modern day large language model. So an encoder decoder, if you look at the way it's presented here, it sort of looks trivial. So it's what's called an autoencoder. We're projecting a given sentence as well as each of the individual tokens into a given embedding, and then from that embedding we're trying to reproduce the original sentence. So we've got this information bottleneck in terms of how we train our model. And of course, you can train this simplistically in terms of recover the original text. The real power comes when you then take the pre-trained model and fine-tune it to do all sorts of other tasks like machine translation, where it's not the original sentence in the same sentence, or perhaps to a paraphrase of that, it's an English sentence to a Korean sentence, for example. Then the last example is a little bit dumbed down here, but just to give you an idea, it's what's called a decoder-only model, where classically it's something like an autoregressive language model, where we're predicting, given a particular context, what is the next word to occur. So rather than I give you the full context and mask tokens, I want you to reproduce the mask tokens, it's an open-ended task in that I want you to continue on from what I've got here. So in terms of the models that you've perhaps heard of, BERT is an encoder, something like BART or T5 are encoder decoders, and GPT-3, for example, is a decoder. Okay, so that's sort of the very basics of NLP 101. So given that, then pre-trained language models are very much at the core of the modern day NLP paradigm, in that kind of the recipe to perform a large variety of NLP tasks, as we had in the earlier slide, is you go to Hugging Face or whatever your favorite repository of different large language models is, you download a model, you optionally do some what's called adaptive pre-training, as in you do more of the pre-training on some domain-specific text to better attune it to that particular text. And if you're doing something like legal text processing, say, you then fine-tune it. So the adaptive pre-training is just more whatever, mass language modeling, for example. So this idea of self-supervision. The fine-tuning is where we've actually got labels which are specific to whatever the task is that we're trying to perform. So something like document level classification, if we're doing spam filtering, say. So we're actually trying to predict those specific labels to specialize our model to perform that particular task on the basis of the substrate large language model. And then, of course, we perform inference over whatever our data of interest is. So I promised to talk about the NLP ecosystem. Given the fact that large language models are sort of very much at the core of modern day NLP, there's a very strong fixation on large language models, as you would expect. And so there's a very strong culture nowadays of particularly the big tech companies, and to a lesser degree, large research organizations like Allen AI, say, to release these large language models. So BERT came from Google, for example. BART came from what was FAIR, what's now MBZUAI. Amazon's in the game. Lots of Huawei, it's not specifically US, of course, release these different language models. And part of the motivation there, beyond some PR purposes, is to accelerate NLP research. Because once you've got one of these models and are doing the fine-tuning, yes, there's some cost there, but most of the cost comes in the pre-training. So GPT-3, I will come to a little bit later. I don't have here because it's not a public domain model, but estimates of the cost to do a pre-training of a GPT-3 from scratch. At the time it was trained, at least, it's in the tens of millions of dollars of compute time. They're not something that you want individual organizations to have to go through themselves. Licensing is interesting. Different organizations have very different philosophies in terms of licensing. So models like BERT, say, were released under very permissive licenses and had a lot of impact because of that. Some of the other ones under commercial or non-commercial licensing. That's a topic for another day. That's a little bit of an aside, a little bit of a case study that I wanted to mention, partly to reflect on this sort of question of ecosystem and sharing of models. So OpenAI is kind of the elephant in the room here that I hadn't mentioned, that has released GPT-3, for example, who have used a very different paradigm of trying to monetize large language models, with some success, to be fair. I'm not trying to criticize OpenAI, but so rather than releasing the model, they've made GPT-3 available on a paid basis for organizations to be able to play around, including being able to do fine tuning of the GPT-3 model. And as a result, GPT-3 in research circles has had much less impact than some of the other models, simply because you can't download it and play around with it and build on top of it. And kind of a very recent exemplar of that is in the context of text to image. So generate an image given a textual description. So I've got here some exemplars from DALL-E 2 from OpenAI versus Stable Diffusion. I'm sure you've seen various examples of these over the last couple of months. They've kind of been doing the rounds on social media. So I sort of did the obligatory generation for the prompt AI researcher on a bicycle. DALL-E 2 has been a lab coat. I'm a big cyclist, just as background. Stable Diffusion is sort of very much more the tech pro look, I guess, with a slightly weird handlebar, but impressive that just given that prompt, it can generate these images, and it obviously has its own ideas about what AI researchers look like. The point here, though, is a perhaps unsurprising but fascinating thing that's happened is Stable Diffusion was released by Stability.ai, I hadn't mentioned, but was in the previous slide, a month after DALL-E 2, which made a big splash when it was first released about 2 months ago. What's happened since it was released, though, is remarkable in that all sorts of applications have been developed in a very short time for Blender, for example, in terms of a shader editor for gaming purposes, for Cinema 4D in terms of some photorealistic graphical rendering, for Photoshop, for in-painting and out-painting, for Canva, for graphic design purposes and various other things. And so the list goes on. Because it's been released into the public domain in downloadable form. Whereas for DALL-E 2, there's nothing. You don't have all of these innovative applications that are built on top of it because you can't access it as a standalone model. You can only play around with it in very limited means via the API or through the web interface. So I'm possibly getting to the end of my time, but I want to just spend a little bit of time talking about some of the limitations of current NLP research. It's certainly not the case that large language models solve everything, but because of this strong fixation on large language models, there's an assumption that's sort of built into a lot of work nowadays that you can access a large language model for a particular language for a particular purpose and get task-specific training data. That's obviously not the case all the time, particularly if you're looking at lower resource languages or sort of very specific text processing tasks where there are perhaps privacy concerns or legal concerns in terms of getting access to data. Also, I guess a lot of classification work, the label set is fixed, predetermined, a priori, which if you're doing a more exploratory task, maybe you know something about the sorts of labels you want to use, but you actually want to learn some of the labels along the way. That's much harder. It's a little bit of sort of artificial task definitions, possibly kidding ourselves about what a task really should look like to make it easier to progress research. So an example of that would be question answering, where a lot of the research nowadays is squad style. I'm giving you a paragraph from Wikipedia, say, answer it relative to that, rather than I don't know where the answer is, go and find it yourself. There's a retrieval question and a very real likelihood that there's not a single text that actually contains the answer that you're after. Or maybe it's completely unanswerable. Large fixation on either single or paired document classification or regression problems, or string-to-string translation of sequence labeling. Strong fixation on English. There's a very sharp drop-off for other languages. Documents you want to have reasonable length, so you've got enough context, but not too much. You can't fit them into the input of your large language model. So if the text is too long, you've got problems. If it's too short, you've got problems. There's kind of a Goldilocks length that you're after. A lot of the tasks we still perform at the sentence level for things like machine translation, say you don't do it at the document level, so that has implications for the coherence of a document level translation. Say text is clean and homogeneous. Twitter is obviously not a safe place for NLP. And this is possibly less of an assumption nowadays. Things are getting more and more multimodal, as we had in the case of Stable Diffusion, for example. But there's still a sort of strong fixation on text to the exclusion of other modalities, unsurprisingly. Evaluation, not sort of in terms of user experience or sort of cost of error, kind of embedded evaluation in terms of specific tasks. So kind of test tube evaluation still. And, you know, IID assumptions and assumptions that there's no temporal shift in the data, which causes all sorts of havoc in real-time applications where if you've got a trained model from 12 months ago, even potentially the stream of data that you're seeing now is very different to what the model was trained over. So I suspect I'm running out of time. Let me just very quickly wrap up. So modern day NLP is dominated by large language models. Hopefully you've got a bit of a sense on the basis of this talk of what I mean by a large language model. And this paradigm of pre-train over some textual corpus and then fine-tune to a specific task. Lots of pre-training, a lot less fine-tuning. A lot of the acceleration has been driven by not just the fact that we have large language models, but they've been released into the wild, particularly for research purposes. So yeah, the sharp uptick that we've seen in performance over different tasks, a lot of it has come from this sharing culture. And at the end, we talked a little bit about perhaps some of the myopia of NLP research. And that was all that I had to say. Thank you very much. Again, apologies for the slightly surreal setting.
Thank you so much, Tim. And I know normally it's our practice to leave the questions and discussions for the break, but logically, Tim will not be available during there. So I wanted to at least open up a few minutes in our schedule for the audience here, or some of the students that have just newly joined us, to ask any question you'd like to our speaker.
So the question is that not all the time we need to use this big language model. Sometimes maybe simple traditional models are already good enough. So is there a way that we can decide when to use the complicated resource consuming model, but when we don't need that?
Yes, so let me repeat the question. So I'll repeat the question so it's captured on the microphone. So Professor Chijan's question was, when should we be using the large models, or when is it preferable to use a simpler model? Is there a way for us to tell?
So it's an excellent question, very topical in NLP at the moment. I mean, a simple answer to that is, well, for languages where you don't have them, or for text types which are far removed from the sort of text that large language models tend to be trained over, which is things like dumps of Wikipedia and book or newspaper corpora, sort of fairly sort of general text. If it's sort of something very specialized, chances are the vocabulary is going to mismatch apart from anything else. So the tokenizer will be ill-fitting to what you're trying to do. I mean, another of the concerns is if you're in a context where you need to have high model reliability, as in you need to be sure of particular behaviors of the model. One of the risks, of course, with these large language models is, particularly if you have a 200 billion parameter model, like some of the recent Alex TM models, it's very hard to know what the model is doing. So providing sort of safety guarantees, say, is a very hard thing to do with large language models. So it's very much a use case based question, I think. But also large documents. So a lot of the legal NLP work, for example, it's the classic bag of words, TF-IDF way to support vector machine models actually often do better than the large language models, just because they struggle to capture a 10,000 word document that has the full proceedings of a legal case. And
that answers Professor Chijan's question. Thank you, Tim. Any further questions from the audience? Okay, go ahead, Baron.
So I have a follow-up question. So do you think that in this safety critical scenarios, language models have to be substituted with something else, or you think there is a path for updating or changing or somehow using these large language models where safety is paramount?
So to repeat the question, Marilyn was asking about whether there are ways to incorporate language models in so-called critical situations where safety is paramount, or perhaps is that inadvisable? Maybe that's the question.
Yes. So and there's a lot of work on doing post-processing or sort of post-training, I guess, as distinguished from pre-training of these large language models, consistent with the pre-training paradigm, to do things like better calibrate the model in terms of the probability distributions that it generates, or debias the models in different ways. And what you often find is, you can to some degree calibrate them and to some degree debias them, but they're such large models that it's hard to do it post hoc. So what we really need to do is embed some of these methods, depending on what the scenario and what dimension of safety it is you're interested in, as part of the pre-training regimen, so that you don't kind of have to mop things up after the fact, or sort of try to wrestle the model sort of to perform in a sort of more predictable way. And that's very much an open research area.
Okay, I think with that, let's thank Tim again once more for the welcome.
Thank you very much, Kamsahamnida.
Great.
Talk before a break right after this. Right now we've got Maran Al-Shadeva, who's currently the director of machine learning at Genesis Therapeutics, working on AI and biotech. Thanks for speaking, Maran. Take it over.
Thank you, Willie. And first of all, I want to thank the organizers for inviting me to CASL workshop. It's great to see a lot of friends, former lab mates. And I'll try to be short to not stand between you and the break. I'll talk a little bit about AI and drug discovery and what we do at Genesis Therapeutics, where I work primarily on machine learning. So my talk is going to be split into 3 sections. In section 1, I'll talk a bit about our company. A friend of mine from CMU mentioned that what they know about Genesis Therapeutics is just a company where Marwan works. So I'll try to give you a bit more than that. Talk a bit more about what we do and who we are. And the second part, I'll talk about the platform that we're building internally. And unfortunately, compared to a lot of research talks before me, I have to be a bit succinct on the details because a lot of this is proprietary. So it'll be a bit of a high-level overview. So hopefully, I will not disappoint you too much, but give you enough taste of the problems that we work on. And I'll be happy to talk more offline. And finally, I'll conclude with some research challenges and opportunities that we see in this space. Drug discovery is a very complex problem. It's not just a single kind of benchmark or task that we can solve with machine learning. There are multiple parts in a pipeline. I'll try to tell you what are the most challenging aspects of it. Also, first of all, Genesis Therapeutics is a vertically integrated AI plus biotechnology company. And by vertically integrated, we mean that the goal of our company is to really start from an idea of a therapy for a disease and go through all the stages of drug development, bring eventually a drug to the market, and try to go through this timeline as quickly as possible. To do that, we try to build a very interdisciplinary team of top AI experts, software engineers, and proven drug hunters with a lot of expertise. So our company reflects that, and our team is split roughly into 50-50 AI R&D team, which is based in the South Bay Area, and also a biochemistry team, which is based in San Diego. We also work with a large network of CROs or contract research organizations around the world that help us run a lot of chemistry and biology experiments, curating data. Our approach is building this vertically integrated company And I think there are a lot of companies in this space that try to approach the problem slightly differently. So they try to build AI companies for biotechnology where AI is used essentially as a service for one of the components. And I think that some in a bit of a disadvantage compared to us because some of the collaboration that happens internally at our company is just not possible when they try to sell AI as a service to other companies and rely on that. You know, as given by some of the internal and external points of validation on the business side, we managed to secure multiple partnerships and important deals, such as the Genentech deal in early November 2020, just a year and bits after the inception of the company, which was a spinoff from Stanford. And then later that year, we raised a pretty massive Series A and generated a lot of interest from the investors. More recently, in April this year, we signed a deal with Lilly. So we have a partnership with them. We're working multiple drug programs and where they use our technology. So apart from these partnerships, we'll also work on multiple programs internally. So essentially, we're working on drugs that we will fully own as a company. And just to give you an example, our platform that we use allowed us to get literally within 5 months to a very promising lead compounds. And I'll talk a bit more what that means in a second, which typically takes a couple of years in the industry. So perhaps this is the last slides about the company, which I'll move on to what we are doing in terms of our technology. But we're a small company, so we have to be very focused. We're laser focused on a very specific problem in drug discovery. So our goal is really to enable access to novel chemical space that will allow us to unlock the highest value medicines that we can design for patients. And on the technology side of things, right, we focus on 3D graph AI technology, which I'll talk in a bit. We strictly focus on so-called rational or structure-based drug design, which means that we try to look at the structures of the proteins or enzymes as targets, and we try to figure out how to drug them by looking at the interactions and predicting what kind of interactions that our medicines would make with these targets. And finally, we try to innovate also on the organization building level. As I mentioned, we have this multidisciplinary team where we're building processes internally that allow us to efficiently collaborate. So in terms of the strategy of the company itself, we try to take minimal biological risk. We work on diseases which mechanisms we already know. And the mechanisms could be known for decades. But the problem is that drugging the responding targets has been notoriously hard. And we believe that with the technology that we have today, with the computes and a lot of advances in AI, we will be able to crack these problems. We also are trying to bring as much things in-house as possible because we believe that this collaboration that we're able to establish within our team is paramount for successful drug discovery. And finally, we select very strategic alliances with companies that we believe can help us validate our platform. All right, so I'm going to talk now a little bit about what the AI platform is and what's, how we view what are the steps that we're taking. But before I go into that, let's start with Drug Discovery 101. For many of you, I believe drug discovery could be a topic that you're hearing for the first time. So what is a drug? That's the first question. A drug is a medicine or any substance which has some physiological effect or therapeutic effect when it is ingested one way or the other or introduced into the body. So essentially any chemical compounds can be a drug. And how do drugs work? Well, drugs elicit these effects, these therapeutic effects, by essentially fitting their shapes into the three-dimensional structure of the protein or enzyme targets, which you can see an example on the right. So the gray area, the shaded area, is this large macromolecule, which is a protein, And then the colored molecule, small molecule, is a drug that fits into this pocket nicely and essentially locks itself there. And by locking it there, you can use the analogy of key in a lock, right? You insert a key in the lock, some keys would fit, other keys would not. And keys that fit could enable or disable the activity of it. So by enabling or disabling the activity, they will disturb a certain biological pathway and, for example, suppress growth tumor. This is very high level, but the next question we can ask is why and how do drugs bind to targets? Right, and protein plus ligand, where ligand is a technical term for small molecule that binds to protein. So this binding process is very complex, but essentially it boils down to figuring out a configuration in the state space that is energetically favorable. So in other words, the system converges to some local optimum and stays there for long enough time if the energy is low. So essentially, we're looking for small molecules that would be able to interact with the protein such that final state of the physical system is going to be low energy. Right? And in general, binding is a very complex process, and simulating this process is extremely non-trivial. It requires a lot of computation, and it's very expensive, even for a single molecule. Now, the problem is that the universe of drug-like small molecules is extremely vast. And it's unclear how do you even approach this problem, right? If you want to do structure-based drug design, at the same time, you want to be able to enumerate somehow and search through the space. And there are more than 3,000 undrugged known targets with validated biology. And we don't have the right tools as of now to be able to solve all of them. So the standard methods known as high throughput screening typically try in parallel a lot of different molecules. So people synthesize them and then they run them through experiments and then they look at experimental binding data. Unfortunately, as you can see, it's orders of magnitude smaller than the possible space, and it's unclear which drugs to select through the screening in order to be able to identify some drugs that would be turned into viable drugs. The other disadvantage is that it doesn't use any structural information. So that's currently one of the industry standards. And our goal is to move away from now, the availability of structures, well, as I said, that we need a structure to be able to simulate in the first place, the binding process, even though it is expensive. And the availability of the structures is growing over time. So there are so-called protein database structures that are available publicly, and there are a lot of new EM structures that are being added over time. And the number is exploding with AlphaFold. Now, technically, get a structure for any protein that will be roughly accurate. Some of the proteins of interest, the structures that AlphaFold outputs are not as accurate in some of the parts as we want it to be. But still, it's a great advancement. And we are coming to a situation where we do have access to a lot of the structures which could potentially enable this structure-based or structure-based drug development. But the question is, how do we leverage these 3D structures, and especially how do we find the small molecules, given that the computational problem is so complex. Now, AI is a pretty wide area and a pretty wide umbrella, right? And we can get inspiration from the advancements in AI in vision and language. These areas have been already revolutionized by deep learning and new neural network architectures, and the synergy between massive amounts of data sets that were available, as well as the important advancements in the architecture design. Right? And as well as the advancements in massive pre-training. So these are the 2 pillars of modern machine learning that are driving progress in these areas. The question, though, is how do we actually take those advancements can adapt to this complex scenario where we have biological systems, we have simulators, we have access to some data. Experimental data is extremely expensive and hard to acquire. So what do we do in this case? And the approach that we take in Genesis is driven by 4 pillars. Right. So the first pillar is molecular generation. Right. So the first step in drug discovery is that is required in order to pick the molecules. Right. We need to be able to enumerate space. We need to be able to generate molecules that we can pick potential drug candidates from. And to do that, we use controllable and scalable molecular generation techniques, right? Where essentially we start with some initial molecules, and then we allow our system to generate new variants and variations that essentially explores the part of chemical space of interest. And I mean, by controllable, I mean that there are multiple parameters that we have to incorporate, because certain molecules cannot be synthesized, or synthesis is very complex. There are a lot of logistical questions around that. And all of this needs to be taken into consideration. The second pillar is dynamic potential net. This is our scoring and ranking method used in Genesis. So it's a graphic neural network that can operate on different input modalities. One type of the input modality is in the slide, which is a planar 2D graph, right? But we've moved away since the inception of the company from that modality more towards 3D graphs and also oral. Finally, the last 2 components are the MLMD platform. Right? MD stands for molecular dynamics or molecular simulation, where we actually look at the molecules and simulate how they interact with proteins. We have different simulators that have different computational requirements. So some of them are more expensive to run. Some of them are less expensive, and we use that data and to feed back into now.
Good question, Aaron. When you say physics-based deep learning engine, is this merely valid physical confirmations of the molecule, or is there more to it than just confirmation, which is like angles and positions?
So by physics-based, I mean that we incorporate physics-based kind of priors or information into the model itself. We do look at the confirmations of the variants and as well as sort of their dynamics over time. So if you look at a single confirmation, it's essentially a snapshot, right? Picture of the movie, right? But what we are moving towards is analysis of full movie interaction.
Now that's an interesting question, because motion is also covered in the molecular dynamics component. So where do you differentiate, if overfitting is concerned, right? Where do you differentiate between what motions go into your upper left model versus what motions go into the upper right? Is it based on granularity, like we clearly showed at the level of like alpha folds and beta sheets up there? So I'm wondering if that's part of it.
That's a great question. So, and not only overfitting is a concern, but also the simulation itself is a concern because it's computationally expensive. So most of that motion goes back into a bright corner where we simulate and we collect a lot of data, and then essentially we try to distill this information into a suite of models that we run at different speeds and different scales. It allows us to, use this at scale.
I see. So does that mean you even consider like not just the full MD simulation, but maybe even coarser models like the ball and spring types of models?
Absolutely, yes. We are looking at the coarser approximation, as well as on the other side of the spectrum, we're looking at quantum mechanical simulations.
All the way down to that level.
And finally, we have a data engine that we're building internally. So essentially, we're moving towards this flywheel, which is probably Tesla has built, right? Where you have a fleet of cars that goes out in the world, it collects a lot of data, and feed back in and iterate. Right. So the components that we're focused on, right, is this 3D structure-based AI. So all this data has to be collected from simulations as well as real-world experiments. Use them together. We use a lot of unsupervised learning in order to train with generative and experimental models. And we also have active learning and vision optimization, which allow us to figure out which data to actually label. Right? We have a lab, we run experiments. So So our platform is built to learn from, as I mentioned, multiple levels of granularity of the data, right? So, and as a first step, we started with pre-training. So we're essentially taking the recipe that has been so successful in natural language, computer vision, pre-train, and then fine-tune the model, and we apply that in, with a lot of asterisks here to drug discovery. Right, so we pre-train on massive amounts of data sets. We use a lot of rich data sets for that are available for certain proteins that are well studied and used by other companies, available publicly or proprietary databases. Also use a lot of extra data such as ADME data, toxicity, and other of different molecules, as well as QM data and data from other types of simulations that we run. And we feed that into our dynamic dimensional net that analyzes the 3D structure, that analyzes the protein motion. And essentially what we're after is learning representations, not just of molecules and proteins, but really molecular interactions between the ligands and proteins. So, and finally, we apply this AI to novel targets. So the targets that we're working on are scarce. There hasn't been, many of them are first, many of the drugs that we are designing, we're aiming to design are going to be first in class, which means that there is no known drugs on the market. And therefore that have to rely also on some type of transfer learning, right, to be able to transfer data for the final component of the platform is human AI collaborative approach that we're taking within the company. And this slide demonstrates real data and real progress over time from March 2021 to roughly end of 2021 and early 2022, where we're able to go through the cycle of molecular generation and then scoring, ranking, and then generating new ideas and then closing this loop with a human in between, right? And this human are actually chemists and biologists that in the lab that sort of orchestrates and participate in every part of the process. So as a result, we're able to start with a pretty rough so-called scaffold or part of the chemical space and refine it all the way to some drug candidates that are extremely potent for the target. And all that was done in pretty short time span, as I mentioned, 5 months ago. All right, so just to conclude, I wanted to mention research challenges and opportunities that I think are extremely important in drug discovery. So the first one is the fact that drug design is a very multi-parameter optimization problem. There are a lot of very strict requirements of what drug candidates can have to be safe, they have to be non-toxic, they have to be effective. And this results in a very massive multi-parameter search problem, which means that essentially there could be tens of different of these characteristics that we're trying to optimize at the same time, right? That's extremely challenging. You can try to kind of explore part of the chemical space, which may have high efficacy or high potency of the drug, but at the same time, it may not be safe, right? And we have to design molecular generation and ranking methods with very strict requirements in precision and recall of these methods. The second one is that there's strong need for out-of-distribution generalization. By definition, I want to design novel drugs. Novel drugs can't be very similar to drugs that are available in the training data that we have. So we have to kind of bootstrap ourselves out from this and make sure that our models are reliable enough when they're trying to make predictions further away from the training data set. Third one is the methods have to scale to billions of compounds that we screen routinely on a weekly basis. And accurate simulation of even a single molecule interacting with a single protein requires a lot of compute. So we won't be able to scale the most accurate and precise methods to the entirety of molecules. So I have to develop methods that are multi-tier and trade off sort of elastically accuracy and compute. And finally, there are some real logistical challenges when we're trying to select and synthesize drugs. might be surprised by supply chain issues affected us and our company. Building block availability of different chemical compounds have had a very tangible impact on the drug discovery timeline of our company as well as other companies. And our methods have to take that into consideration, right? Both molecular generation platform as well as the way that score and select molecules at different stages of the drug program. So all of these are interesting questions, and interesting to see how we can address those by developing methods. So, okay, so with that, I wanted to thank you for your attention.
Okay, so we're a few minutes behind schedule, so let's do this. We're gonna have a break right now, just a 10-minute break, so we can get back onto the schedule. But I'd like to ask a few questions for Marwan. Let's talk to him during the break. I think I and probably others have a few questions, and we'll be back here in 10 minutes to start the last round for.
Welcome everyone to the last section of the CASL research workshop. So we have one of our own, Sam, and from MBZUAI here. So Sam will talk about federated learning stuff, which is
So yeah, thank you for putting this workshop together. Thank you for inviting me. So what's the topic of my talk today is this following work we did a year ago, titled Fair and Accurate Federated Learning under Heterogeneous Targets with Auto Dropout. So this is a joint work now it works. So this is a joint work with collaborators from Samsung and Facebook. So Steve, Mario, Stelios, Ilias, and Nick. So first, let me just give you a high-level motivation of what federated learning is and why we do things a certain way. So originally, how we would implement your machine learning model, let's say like intelligence, what you would do, you would just collect all your data to one centralized machine, and then you train, let's say on a single GPU, and you would train some small model. But over the time, we moved from this local solutions to cloud solutions, as much of machine learning success relies on these two key pillars. One is large-scale training infrastructures, and the other one is the vast amount of training data. But when it comes to the data, we have to consider the source of the data, which are usually users, which might be negatively affected due to some privacy implications of this data collections. On top of that, we have several privacy initiatives, both enforced for government and private entities. And at the end of the day, this might lead to actually unavailability of the data. Therefore, we lose this second important pillar. So, and this is where the proposal for federated learning comes into play, where the proposal is, let us just now move compute to the clients. And what we're going to do at the clients, we just perform some computation over the local data. Then we aggregate them, and what we have here is some kind of a global orchestrator that's going to take care of the aggregation, but it's only going to see the premise here. It's only going to see the aggregated information. So the hope is that it's like we keep our data in a sense private. But now with this, we have available. We kind of keep the second pillar, which is the availability of large amount of decentralized data. But now the question is, what are we going to do on those devices? Suddenly we might lose access to the very powerful compute, and also what are we going to do with the type of data that we work with. So when it comes to just to show you a few applications, for instance, the ones that are already in production, this might be Apple's Hey Siri or QuickType, Google's Hey Google or Gboard, but maybe like more important things that we are kind of looking for the future are the applications where traditionally you have quite a lot of data, but usually they are private, so you kind of can't directly access them. And this might be, let's say, like smart home applications or some fintech applications. And the setup that I'm going to focus on today is something called cross-device federated learning, where we have millions or hundreds of millions of devices. Each device has small amount of data. What they're trying to do. They're trying to, under the orchestration of the global server, they're trying to train model or train some recommendation model of some sort. And what is also important here that once we're going to train this model, we're also going to deploy it to those devices. So the typical loop for this setting looks like this. So we have some kind of an estimate of the global model. We send it to the clients. We ask those clients to perform some computation over their local data. We just aggregate the updates. And then this aggregated value, usually just simple averaging, is used to update the global model. But one of the key challenges here is that the devices that we perform computations on are heterogeneous, and this is something that we have to account for when we are designing our training. So usually what people do is you have all this variability of the devices from some, let's say, low-end IoT devices all the way to some last generation flagship devices. So the standard thing that people would do is, okay, let me just accommodate my model to the lowest performing client. Or what I'm going to do, I have to train the same model, because this is kind of most of the time only thing I know how to do. So what I have to do here is either I'm going to drop low-tide devices, or I actually have to train a very small model such that it fits all the devices. What happens then is there are several drawbacks of such approaches. First, when you're just naively dropping low-tide devices, you might have quite limited participation. And this might be quite a bit of an issue for federated learning, because what we usually assume is that all those devices, they have heterogeneous data, and majority of the data is important for training. So you can have actually a lot of bias due to unseen data. When you, let's say, okay, when you say, okay, I'm going to just train a very, very small model, you can actually have very degraded performance for those like high-tide devices, and they might just not be willing to, let's say, participate in federation, or actually your model just perform overall badly because it doesn't have enough capacity. So what we set as a goal for this study is we would like to overcome these challenges. And the first kind of thing that we're going to focus on is we want to have a fairness in participation, meaning that everybody can participate such that our model is trained on all of the data. But on top of that, we want to guarantee the competitive performance for all the devices when we're considering their local or network constraint. So how are we going to achieve that? We first, kind of a naive idea is just, we're going to drop the requirement that every single client has to have the same model. So what we're going to do for those lower tier devices, we're going to deploy something, some thinner models, where we're going to dynamically adapt their width such that we accommodate those models to current like memory constraint, computational capabilities, load, and so on. So, but how to achieve this? So in order to achieve that such model that can be like easily prunable without actually need for the data, what we're going to do, we devise the technique that's called order dropout. When we put it together next to, like, so here I have a standard form of fully connected neural network with 2 hidden layers, where what we usually do for random dropout. So for all the layers that we apply random dropout, we just take one neuron. With some fixed probability, we either drop it or keep it. And by dropping, I mean that we actually remove all the incoming and outgoing connection. And the main goal or purpose of this is to kind of prevent co-adaptation. And then for the deployment, just gonna average all the weights, and we're gonna use anyway the full model. So when it comes to order dropout, we use similar but different technique where the kind of the style of our dropout is structurized. So what we have first, we have a set of relative submodel width. So these are some numbers between 0 and 1, which are the width that we would like to train our model on. And then we have a distribution over this width. So you can think about this as, let's say, like uniform distribution over all this width that we are trying to train on. And then what we're going to do for the training, we have a full model. We sample from the distribution. Let's say here we sampled 0.4. That means that we only keep 40% of the network and most left part of the network. And this is what we're gonna, in training, this is what we're gonna evaluate forward and backward pass on. Then for the deployment. Now, because the way how we train, there's actually very straightforward way how to deploy these models. We can actually just accommodate width of the model based on the device that we are trying to deploy to. So just to give you, so this was like hand wavy motivation, just to give you actually the actual, let's say, theoretical reasoning why this makes sense. Let us consider the following task. So let's imagine that between our features and output, there is a linear mapping that I'm going to denote by A. So if I'm just trying to train on, let's say the data comes from a uniform ball. So if I just train this type of network, which doesn't have any activation or biases, just a linear neural network with one hidden layer, I'm going to solve this problem only if this guy exactly recovers the target model. Now, the question is what happens if I embed the order dropout into this layer, meaning that I sample actually every width with non-zero probability. What we actually show in the paper, and maybe it's not surprising because I show SVD here, is that network, the only solution that is optimal to that network, meaning that we solve the problem, is the SVD solution. So meaning that I take any width, on that width, I have to recover, let's say on width 2, I have to recover the best 2-rank approximation of the target mapping. And not only that, it's also not only like the set of optimal solution is only SVD, but you can also show that once you run SGD on this problem, it's actually going to converge to the solution. And we can show it both practically and theoretically. Now, the question is what we're going to do once we combine this with federated learning. So how are we going to combine these two techniques? And combination is pretty straightforward. So we have a set of devices that we want to train on. What we're going to first do, we just, as always, select the architecture. Then we select the width that we want to train on. In order, for instance, like here, for a given model, let's say we have Resident 18 or Cypher 10, then each width corresponds to a different model with different number of parameters and different computational requirements. Once we have these, we group the devices into several tires, let's say here 3, and then we assign each tire with its P max, which corresponds to the maximum width that tire can work with. Then for the training, we use any out-of-the-box federated learning technique, with the difference that what we do, we have some subset of the devices that are available for training. We're going to do with our current model, we just communicate the models to each device. But the difference is here that the model that they receive is accommodated based on their constraint. What we're going to do here, we're going to run as for standard optimization techniques for federated learning, we're going to run some local methods. But here, importance is that you run the method with order dropout. Once you run several local steps, you obtain the new model, aggregate, and you obtain the new model that's going to be distributed in the next round. Then for inference, as I already showed, you can just adjust the model based on the current client capabilities. And what's actually nice thing about this is, imagine that I already deployed, let's say I had the device that was capable of fully accommodate the model that I trained, but let's say now my battery level is low and I can't really afford to evaluate from model because it's going to just drain my battery. What I actually can do because of the structure, how I train the model, I can just decrease the size of the model without any fine tuning, and I can still get some reasonable predictions. For the experiments, let me just show you. So this is the experiments where we don't consider federated learning baselines. What are here, where we don't consider federated learning, what are here our baseline is for every width, we just train the model that we compare to the single model that's trained end to end. So here we have 5 independent models. And what we have here is our model trained with order dropout. So this is a single model evaluated with 5 different widths. So we can see is actually, it's pretty much almost like, so this is a 1 standard deviation. So up to 2 standard deviation is matches the performance of this best single model. But what we were originally hoping for that because of the regularization we were hoping that we actually hit the better regularization. But the thing is, on these tasks that we consider, there are actually might be the thing that the models that we are trained already highly unfit to the test data. So we are right now conducting the experiments on large data set that could resolve this, let's say, small issue. Another thing that we tested is what you can maybe kind of argue that what if the technique that I propose is not really meaningful, and it's actually that there is some kind of an interesting property of neural nets that you evaluate on any width and it would still get a good performance. So what we did to test it out, we just take fully trained networks, so the full network, and we get those submodels just with random dropout, such that the networks have the same number of parameters. And what you see here, that actually the drop of performance is quite significant, and this performance up is due to our dropout. It's not just some naive property of every neural network. Then the last thing that we tested here is the scalability, meaning that if I train on more width, actually the performance along those original width preserves. When we move to federated learning, what we compare to, so with federated learning, there are not many good baselines that could handle heterogeneous devices, and one baseline that was commonly considered in literature is that you apply random dropout to train those smaller models. But the thing with random dropout is that once you take more than, let's say, like 20% of random dropout, that the model performance is completely destroyed, and that's what we actually see here. So the thing is, you add capacity to your model, but because you have many clients that actually can't, let's say, run the full model, so they actually have to train on only 40% of the width, you see that the performance might be with the increasing width might be detrimental, which is not the case for or the dropout, because due to its natural structure, you just kind of keep it just squeezing the knowledge towards the left of the network while trying to add the extra, trying to squeeze the extra knowledge towards the right of the network. And this is kind of consistent across different baselines. The same once we move from the centralized setup to federated learning setup, still the scalability is preserved. So if we try to evaluate the network, we try to train the network on a high granularity of this width. So we still that the performance along the width that we intersect is preserved quite well. So okay, let me just quickly summarize. So what we propose, so what we first discuss is this challenge of heterogeneous devices in federated learning. We propose this new technique called early dropout that as a technique to enable heterogeneous training. And finally, I've introduced a fjord, which is the federated learning version of early dropout. Right, so with this, thank you. Happy to take questions.
Thanks, Sam, for getting us on schedule. I guess we have 1 minute for a question.
Quick question, very cool idea to order the dropouts. If I understand correctly, it seems like the different principal different, I guess, like SVD components, different number of clients will contribute to it, right? So
yes.
The largest components will be contributions from all clients, and
the smallest will be from all clients. This kind of towards right of the network that's on all clients.
Do you notice like the your behaviors of the model when you intentionally kind of?
Oh, so yeah, that's a that's a great question. So what kind of happens? Let me just go quickly back. So what we did in this experiment, for instance, like here, what we did, we just actually split all the clients to like there's like 20% of clients that only can fit this model, 40% so another 20% that can fit, that this is the max that they can fit. So, and what we did to kind of exactly try to see what happens, for instance, when there is actually many, like majority of clients, let's say like 80% can only store this model. So what then happens is actually you keep the performance of this guy because the training is kind of the same, but you can't really recover this very good performance right here. So we have like kind of a technique to kind of a bit try to improve the performance towards the right of the network is to actually combine fjord with random dropout, but with a small amount of random dropout, kind of trying to fit the bit of the knowledge towards the right. But what you generally see is because the right side of the network is not updated by many clients, you don't see that good performance. But the good thing is that this kind of this curve, increasing curve, is preserved. So it's kind of, it behaves as expected. That was a good thing.
Thank you, Sam. I think since we are on schedule, let's thank Sam and link this over.
Can you hear me now?
Can hear you.
Yeah, okay. Thank you, Billy. So my name is Xiaodan Liang, and today my topic is about grounded multimodal pre-training and applications. Okay, so multimodal pre-training models using large-scale pre-training over images, videos, text, and audio data has some state-of-the-art performance on numerous downstream tasks like image generation, image text results, and image captioning, real question answering, and open set recognition. My research focused on answering 4 modeling questions: how to achieve fine-grained alignment, how to use more modalities.
Hey, Xiaodan, can you switch to you are showing the presenter view on the screen right now. Can you show you switch to a presentation view?
Yeah. Okay, so let me check. Can you see now?
Yeah, that's much better.
It's much better now.
Wait.
Oh, I see. Yeah, let me check. Can you see now?
Yep. Yeah.
It's okay now?
Yes, good.
Okay. So my research focus on answering the 4 modeling questions. So how to achieve fine-grained alignment, how to use more modalities, and how to efficiently use large-scale noisy data and develop knowledge-enhanced architectures. So ETS can support open world detection simulation, 2D image generation, fashion designer, and human-robot interaction. So character vision language models mainly fall into 2 categories: dual stream models and single stream models. So the dual stream models like Clip and Align have used heavy separate encoders for both modalities, but the modality interaction part is usually very shallow. The architecture allows flexible use of different encoders and their inference is efficient for downstream tasks. However, this model usually compute image test similarities with global features and lakes of fine-grained interactions between image and text. On the other hand, so single stream models use light encoders and heavy interactions and often performs better on their tasks and require deeper module fusions like visual question answering. So we have a paper on ICLR 2022, and our work is about how to develop the dual stream models and propose a multimodal interaction mechanism to capture the fine-grained representations. Here is our framework. Our framework is named as a Philip. So a Philip is a dual stream model as shown in this model, and in the contrastive loss, previous works like Clip encoder each image and test separately to get global features, and then computer cosine similarities between the 2 global features. However, this model neglects fine-grained interactions between the word patch alignment. So to learn a token-wise alignment, we propose a token-wise max mean similarity. In a max step for each token in one modality, we compute its similarities with all tokens from other modalities and select the largest one. And in the mean step, we use a mean operation and aggregate all token-wise similarity use a global one for each image pairs. So we can replace the original similarities in clip with this one. We still use a contrastive loss for pre-training. So we first feed the images and test to both encoder to get a token-wise representation, and we get a patchwork similarity metric, and follow the max mean strategy to get a similarity between the image and test. Finally, we can pre-train with the contrastive loss based on the similarities. Since the cross-model latent interactions rely on the token-wise representation, so it can be very inefficient in terms of communication, memory, and computation, especially when the batch size is very large. So we propose to use top 25% tokens with large similarities within each local patch. So besides, we also reduce the embedding size and use half precision features for communication. With all this optimization, Philip is only slightly slower and occupies only slightly larger memories than Clip. We also collect a very large data set from the internet, from called Philip to Philip 300 million. And besides, we also use 3 other public data sets, CC10M, CC12M, and WebCC. Finally, we use 340 million image test pairs for pre-training. It's slightly smaller than the data set used by Clip, but much smaller than the data set used by Align or Google. And this is our performance on the image classification. So we evaluate Philip on 12 different downstream data set. As we can see, Philip performs much better than Clip on both their short and linear probing settings. On the retrieval tasks, and Philip also retrieve the sort high performance and outperforms Clip, Align, and other data and other models. We can see also from the visualization results, Philip can accurately align the image and the patches and image patches with their corresponding catcher names. Besides, we also use a fine-grained cross-model pre-trained model for image generation. As we all know that DALL-E2 is very popular in generating high quality natural images. High quality natural images, but it fails to add details in images. So we propose a unified cross-model fashion designer with a new patch level, pi level, and gamma level alignment. It can handle well the text to image, text to sketch, text and sketch to image, and also test the image part to image generation. To learn a semantically accurate alignment between the visual and text features, and leverage a very expressive cross-model codebook to incorporate the fine-grained text information. So we propose a new model named Amani. In our first stage, an image mask and the text encoder is used to encode an image mask and test repetitively. And the image encoder is used to generate a gamut and to facilitate training while image reconstruction. And the mask and the test token are also aligned by using our proposed mask clip. And the most relevant test for mask is fused with the image token that corresponds to the mask token. After fusion, the token is quite nice to obtain the Z, and finally, a cross model code book is obtained by obtained after training in the separately in the second stage. So the test control signal and real control signal are used as an input to generate a sequence of token. So these are our qualitative image generation results. And we can see the model can successfully generate images given the test, sketch, and the image part, and to generate a very high fidelity image. And this is we also compare our model with TeddyGAN, Cogview, DALI in the qualitative results, and released our new dataset, same fashion dataset. It contains very large scale gamma images and their corresponding test. And finally, our model can well be. And finally, our cross model, our fine-grained cross model language training can also be used open set or object detector. This is our video demo. And because most stereotype object detection methods can only recognize and localize a predefined number of categories. So here we propose a grounding formulation of open world detection by directly utilize the detection, grounding dataset, and the image test pair dataset for pre-training. So we propose a new model named as that clip. A dictionary enriched with a concept of parallel pre-training method for open world detection. During the pre-training, so existing dataset often use a very large, often have a large domain gap and the difference in their labeling space. In order to form a more unified concept space and provide prior knowledge for each input context, we propose a novel concept dictionary to enrich our prompt test during a joint pre-training. To elevate a partial labeling problem for grounding and image test paired dataset. So our DACLIP further readily sample concept from a dictionary as negative sample to efficiently pre-training with the alignment loss. And under that clip also develop a neural language pre-training pipeline. So we first design a novel parallel concept formulation to improve the learning efficiency. Instead of feeding the whole test for into the model. The DACLIP extract its concept separately and parallelly feed them into the test encoder. The parallel formulation can allow the model to avoid the unnecessary interaction between the uncorrelated categories and phrases. And we can also produce a law description for each concept. By converting the detection dataset, grounding dataset, and image test pair dataset into parallel formulation, our DACLIP can be pre-trained our different types of supervision to support their localization and open domain capabilities. Compared to the recent GLIP by Microsoft, our DACLIP model can outperform their GLIP by a very large margin. This is over 90.9% in overall on the LWIS and 12.4% on the real classes. Also, it can achieve better training and testing efficiency. And from the visualization results, we can also see the DACLIP can recognize the more rare and small objects. And by adding, so So we have three different settings. So object 365 go, and we also order dataset from golden gradient dataset and WebCC image test pair dataset. And we can see by adding more unsupervised image test pair dataset, so Redactive can further improve the results and achieve result performance on the Elvis and 30 dataset on open world object detection. This is our home message, take home message on my talk. So we so my group mainly explore large scale grading large scale graded neural language pre-training, and we try to apply them into the open world object recognition and grading 3D 2D 3D object human generation and close editing, and we also have some work on human robotic interaction to investigate how to use our open world recognition models for open world human robotic interaction. So this is our talk. So any questions?
So yeah, for all our virtual talk, we hope to have some questions right away. Let's take at least 2 questions for this section.
So maybe just as a starter question here, in this these perhaps more computer vision oriented pre-training scenarios, right? Has there been any observation that correlates, say, the effectiveness of pre-training with, say, certain architectural properties or the size of the model? For example, one kind of theme that's occurring in the NLP community right now is that past a certain model size, going from, say, the ones of billions to tens of billions and hundreds of billions of parameters, certain tasks that the model will perform badly on or close to random on 1 billion parameters starts to do significantly better than random at 10 or 100 billion parameters. So I'm wondering if in the computer vision community there has been any similar observations that some tasks cannot be done below a certain model size or without a certain kind of model architecture.
Yeah, Sheldon, do you get the question?
Yes. So I think regarding the pre-trained cross model pre-trained models have so very good performance on many downstream tasks. I think the pre-trained data set size and their model size is very critical for tasks, and I think the current most popular models like Flamingo has demonstrated the SOTA performance on over 20 to 30 different tasks. So I think this direction is very promising. But it's not sure. So how will the model size will affect the results? But I think but from other experiments, it shows the larger model size will also will always can induce the better performance.
Thank you, Sheldon. Jerome, did that answer your question?
Yes, that answered my question. Thank you.
Thank you.
Thanks, Sheldon. I think it's time. We are pretty on schedule. So, Sheldon, you are welcome to stay for the rest of the talk. And we thank you again from our side. Okay, so next up will be in distributed training. Thanks, Hong-Yi, for having the talks so early in the US.
It's my pleasure.
You can start share screen.
Sure, yeah, let's do that. Can you see my screen, by the way?
Yeah.
Oh yeah, I can see. I can also see my screen on the on the meeting room. All right, let's get started. Yeah, thanks. Thank you so much for organizing such a great event, and thanks a lot for having me. Today I will basically talk about when will gradient compression be useful in distributed training systems. The title may look like a bit surprising, but hopefully when we dive right in, you will find it more reasonable. This is a joint effort with an amazing group of folks from both academia and industry. And today I will basically talk about kind of like just the 4 points of like what is gradient compression basically, and why we need them, and when will gradient compression be useful in real distributed systems when we deploy them in a real cluster, and how to design basically useful gradient compression for the future applications. So basically, what is gradient compression? So gradient compression is something like this talk will basically focus on data parallel distributed training, and in data parallel distributed training, so the messages that are communicated across distributed nodes actually gradients. So each of the nodes is the basically partition the input, let's say data batch, and the grid is a gradient, and kind of like a synchronize that across the entire cluster. So when the model becomes large, as we can imagine, the communication can actually become a bottleneck. So gradient compression is a technique that actually deployed to kind of like seek to tackle that communication overhead issue. So if we think about that, if our size of the gradient is kind of like a vector, then the amount of communication is that for each of the element we have to communicate like a 32-bit like floating number. So what we can do is that we can sometimes reduce the precision of each of the like element, say from 32 bits to like let's say 2 or 4 or 8 bits, or sometimes we can kind of sample the gradient elements such that we do not communicate over all of the gradient elements. Instead, we just sample k important one, or randomly sample k like gradient elements among the entire gradient elements that are computed by each of the worker node. So basically, why we need the gradient compression? So measured by it has been widely observed in the past literature that if we actually just use like large distributed cluster, and we are trying to train large model. So say in this example, it's coming out of SOSP 2019 paper that so the x-axis here is basically the number of GPUs in the cluster, and the y-axis is measured communication overhead measured by the percentage of the communication that take into the like of the entire iteration. So the percentage of the total time of communication over the entire iteration time. So you can see as the cluster size grows to like 32, something as large as 32, the communication can take almost like 80 or 90% of the entire training time. So that basically means the communication can be actually an overhead in like even in data parallel distributed training. So so we want to basically ask the question. So this sounds a little bit surprising, but if you look into the literature, that most of the gradient compression are benchmarked by either the authors come up with their own implementation, or they just come up with some like a toy implementation. They just write down kind of like a training pipeline, and then after the training, they basically handle the communication by themselves. So we are basically asking the question: what if we just take the method and really try to implement them into what people are using? Let's say PyTorch or TensorFlow, the API they provide to conduct distributed training, and deploy into some cluster, let's say offered by public cloud, let's say like AWS. What will actually happen? So it turns out we're basically just implementing this each of the kind of like gradient compression method we can find. Those are state of the art. We're trying to optimize them very well, or kind of finding the state of the art implementation, and really implement them in like in the real distributed system on the like popular benchmark. So here we can see that we are basically choosing 3 state-of-the-art gradient compression method, specifically Power SGD, Top K, and the Sign SGD. So the dark blue bar here, we call system optimized SGD, is basically PyTorch DDP. So that's just the API, and we just take the like cluster instances from the EC2, which from AWS. So those are the kind of like standard setting we can possibly find. And surprisingly, we observe that it seems the PyTorch DDP always wins in the most of the scenario we tried. So clearly, gradient compression does not work quite well in practice. That basically seems to give us the message. So we want to ask why. Why don't we see significant speedups even like in the practical scenario? So here are a few reasons I want to share. So first reason is basically so when we consider the basically computation graph of neural network training. So sometimes we basically have to compute the backward propagation, and then we have to synchronize the gradient. But however, those operations does not necessarily need to be serial. They can be actually overlapped. So once we compute the gradient of the last layer, we can immediately start the communication of the gradient of that layer. So if we conduct, turns out in practice, like people like the overlap basically are implemented into the API, say PyTorch DDP. So if we basically just conduct that, the communication overhead is largely reduced, such that the space for gradient compression to work on become much smaller. And also, the batch size also kind of like take into play into this like scenario is basically if we use a larger batch size, so computation scales with the batch size, but communication has only to do with the model size. So basically, if we use a larger batch size, the communication overhead becomes even smaller. So that's the first reason. The second reason is basically sometimes a gradient compression can be actually computationally heavy. So so in this example, the backward propagation only takes like over 120 milliseconds. But sometimes the gradient compression can take even longer, or kind of like at least comparable to backward propagation. So the overhead of the encoding and decoding, so basically computing the compressed gradient, can be as heavy as the backward propagation. And also sometimes the gradient compression is not compatible to the all-reduced API. So which basically means they have to only be implemented into a kind of like a less efficient gather API, such that their performance won't be basically comparable to the all-reduced collective communication API. So with that, can we actually build a cost model to capture this in practice? So basically, if we consider the common strategy that's basically called the bucketing strategy, that we are kind of like splitting the gradient into a few buckets based on their size. We can basically cut or aggregate the gradient, and we can actually build the cost models in this kind of like a format. Basically, we're trying to capture the first term is basically how the computation can be overlapped with the communication of the first k-1 buckets. And then we can also capture the communication of the last bucket. So it seems to be a straightforward communication model. And then we can also plug in the gradient compression here is basically new communication cost plus the encoding and decoding cost. So it seems this cost model captures the communication very accurately, at least even with this simple cost model. In kind of like most of the task we tried to experiment in our work. So why this cost model is useful is basically given the implementation and then the cluster and also ML model, and given the bandwidth available in the distributed cluster, we can basically predict what's the compression ratio we actually need to achieve linear scalability. So basically, for instance, this is a quite standard bandwidth we can observe in the distributed cluster. It's basically if we get like 10 Gbps bandwidth, we don't actually need such kind of like a massive compression ratio. So sometimes it seems like just 3 or 4 like times compression ratio will be good enough. So basically, like to summarize, basically, I want to ask how to design the next generation of gradient compression to make them become really useful in practice. So basically, we should focus more on the encoding and decoding cost, as we just showed. So the compression ratio can be important, but not as important as the encoding and decoding cost. And we should also make sure the compression method should be compatible to our reduced API. And basically, we should also focus on the good put. So the gradient compression method should not just crush the model's accuracy. So let's let me walk you through one example, like how a gradient compression method can be useful and how can we actually design a concrete gradient compression instance. So basically, previously people have looked into like gradient factorization. So basically, use the low rank factorization of the gradient. However, the factorization can sometimes become expensive. So in kind of like this concrete example, we want to ask, what if we just incorporate the compression into the training itself? So instead of like factorizing gradient of those 3 layers example, neural network example, so we can just factorize the model weights instead of the gradients like explicitly. So basically, we just train the like low rank network instead of like factorizing their gradient. And since the network size is reduced, the gradient is also basically becomes smaller. So however, the good put there is bad, right? Like if you just train the low rank network, sometimes it's not initialized very well, or the capacity of the network is not good enough. So we can see the large accuracy gap here. So how can we improve that? Is basically, we can look at the network's model weights, and we can find like some of the weights are kind of like inherently higher rank, so that's not quite tolerable to low rank factorization. And some other layers can be actually low rank. So we can basically detect them to decide which layers are easier to factorize. And also, it turns out that directly start from low rank network is not quite desirable. So we can basically start from kind of like a warm up the origin network a little bit, and gradually make them become low rank. So we basically warm up them for a few epochs and factorize them, and basically then start to train the low rank network. And turns out those two simple heuristics fix the good put very well. So now you can see that with incorporating those two techniques, the good puts become much better. And since we are using this method, we do not have any encoding and decoding costs. And sometimes the computation can also becomes faster because we are training a smaller network. And overall, it becomes like the end-to-end communication time can be much better compared to the like even the state-of-the-art like gradient compression method and also the PyTorch DDP method here. So one thing we can see in the like previous work, the factorization, is that we have to basically detect the factorization ratio, the rank we want to use for each of the layer. So how can we make them basically automatic? So it turns out we can use some of the metrics, let's say rank estimation of each matrix layer. So basically each layer's parameter weights to basically detect the rank we actually want to use in practice. And sometimes the number of warm-up epochs can also be important. So here we observe that actually the estimated rank becomes stable in the end of the training. And we can also use that to determine what's the rank we want to use to factorize each layer. And turns out the thing becomes kind of like very interesting is that the rank can actually be solved like explicitly if we don't care about the training speed. So here's the work like from CVPR last year. It's called like LC compression, so which is basically the orange line here. And turns out our heuristic can basically use the rank estimation, can basically be get the results that very close that match very closely to the explicitly optimized rank selection. So basically that means our method captures the rank, the basically true rank we want to use for each of the layer very well. And turns out if we basically adopt the automatic version, we can kind of like compress the network even further to achieve even better compression ratio. So with that, I want to also share a few open problems. So basically, the first is I kind of like only captures the data parallelism in this like talk. So how can we also do like message computing in beyond data parallelism? What will happen in model and the pipeline parallelism? And also, how can we make the entire? Do we have the cost model? Can we use the cost model to determine the optimal compression ratio during training? And for each of the given tasks on each of the given cluster. And also, it seems the entire thing, the message computing, is not quite integrated quite well in the current software stack. So can we actually build one that with high performance and optimal implementation? So with that, that's all I have to share for today. And I'm ready to take some questions if there are any.
I can ask a question. So, right, closer.
That'd be wonderful, so everyone can see the person asking questions.
Okay, hi, Hungry. Thanks for the great talk. So I had one question, which is, if I'm not mistaken, when you implemented Power CD and the other gradient compression, you were expressing them with a PyTorch API. So presumably this gets run in the GPU, but it can have quite a little bit of overhead. And some work, or which is maybe parallel to your own, last year in SOSP, the high press paper had implemented several of these compressors directly using CUDA kernels, because they were saying, otherwise it's very high overhead to begin with. So I was wondering, what was your thinking when you were trying to do the work, and why did you not go down to the level of CUDA to minimize the overheads here?
Oh yeah, I think that's a good question. That's actually a common kind of challenge we basically received in this work. Is basically how can you make sure your like implementation is optimal. So I think that's very hard to that's actually very hard to have a kind of like a guaranteed answer that once we say this implementation is optimal, this other day you can also basically try to use better optimization technique. Let's say, like the example you mentioned, you delve into the kernel implementation level, you find the better implementation. So that's actually something like but the point I want to make here is basically our cost model can still capture that actually. Like for the encoding cost you give me, I can still predict that like how does the method perform. So that's the main message here. It's not going to criticize the previous method. It's just to say, like, how can we capture, can we characterize or find the representation of different like gradient compression method, and when can them actually becomes useful. So like as in the example you mentioned, like if we really implement, let's say Power CD or whatever method in the like down to the CUDA level. So in our cost model, basically the communication can be still very efficient. If we take into the encoding and decoding cost, it can be much cheaper. So that basically means that the method can actually be useful. So like the point we want to make is basically if you take the existing like implementation, right? Like we just take the implementation in the Power CD paper. We also implement that actually the PyTorch system implementation in the original PyTorch version, because that's integrated in the gradient hook in PyTorch. So it seems to be compatible with our like observation. But yeah, that does not disagree with your observation, right? Like if you really push down to the bottom level, I believe that can be that can work well. So that's also related to my open problem here. If we actually find a way to basically kind of like come up with the high performance implementation in the library, I believe we can actually make a gradient compression be adopted more kind of like widely in the industry level like platforms or kind of like products.
Thank you.
Yeah, thank you so much for the great question.
Okay, thank you, Hongyi. So thank you for joining us so early there. So we are going to move on to the next talk by Janelle. Hongyi, you're welcome to stay and listen to the talk. Okay. This is our final talk today. So Janelle is from Google. He's going to tell us about how to optimize, how to improve training from compiler level. Hey, Janelle, are you speaking? You might be muted. Give us a minute to do this.
Hello.
Okay, I think we can hear you just now.
Awesome. All right. So sorry about that. I didn't know I was muted. Yeah. Thank you, Eric, Hector, for the introduction. My name is Jingliang Wei. Sorry, I'm not able to actually go there. But I'm glad to be able to talk to you here. So I'm currently working as a software engineer at Google. I was Eric's student from 2012 and to 2019. So when I came to CMU for grad school, Eric taught me to work on machine learning systems to be able to scale up machine learning training so that we can solve larger problems using machine learning. At that time, I had almost no idea about what machine learning is, but I'm quite inspired by the kind of problem that machine learning can solve and the kind of problem that machine learning will be able to solve if you're able to scale up the model size and the data size. So I started working on large-scale training systems, and I have still been working on large-scale training systems now. So today I'll be telling you about some techniques that we have done at Google in order to scale up deep learning training using compiler optimizations. I think Google has been doing a kind of unique and special route for scaling up deep learning training. So this might be interesting compared to other approaches that other maybe academia or other companies that took for this problem. Yeah, so as system researchers or system engineers, we look for problems by looking at two trends. One trend is on the application side. So I guess this trend is probably already pretty obvious to the audience here. So that we already see the state-of-art model size increase rapidly in machine learning. This is true for natural language processing, but also true in other application domains in machine learning. With the increasing size with the increased size in the model size, we definitely need more and more compute power to train those models, and this requires us to be able to scale up training both in terms of requires more powerful hardware and in terms of more hardwares. Another trend is on the hardware side. I think many of you probably already know that TPU is Google's proprietary machine learning accelerator. So Google see this problem back in 2013 when when they projected that if they are going to serve a simple deep learning application on CPU, the problem simply becomes unaffordable because they would have to double the data center fleet. So Google started designing this special hardware called TPU for serving machine learning inference. This the main idea in TPU is to reduce the power consumption in serving machine learning workloads. So by using TPU, the first version, Google was able to reduce the inference cost by almost 10 times. So since then, Google has also applied TPU to training. So Google has been designing TPUs for both training and inference. So as you can see, in each version, each TPU has become more powerful, and which is shown by the flops per second, the flops per second here, and also many TPU chips are connected using high-speed interconnects. This is called TPU pod, as you can see in the last second column here. So as you can see, over time, the TPUs are becoming more powerful, and more TPUs are connected into a pod. So this means the hardware are becoming more powerful, and there are more accelerators that the researchers or engineers can use to train their models. But this also brings up the question for the software. We need the software to advance to be able to actually use the hardware, advanced power to train large-scale machine learning models. So I think generally Google has done a pretty good job in advancing their software to cope for the advance in the machine learning application and also in hardware's advance. So we can see this trend in some of the open benchmarks that Google participates in. So one of the probably popular benchmark across the industry is called MLPerf. So Google has been submitting to MLPerf since 0.5, which I think is back in 2019, and Google has been submitting since then. I think in back in 2020, which is the first round MLPerf that I had participated in. So Google was winning the benchmark records in 6 out of 8 benchmarks in terms of fastest training time. And yeah, so basically this demonstrates Google has advanced its machine learning software to allow people to use their machine learning hardware to train models efficiently. So of course, those the benchmark here is only represents the standard benchmarks that people use to demonstrate performance, and there people. So this only represents a small fraction of the actual workload running on TPU, but this gives people out externally gives people a sense of how the TPU is performing in training machine learning models. So in terms of so on the software side, I think a major technology here is the compiler optimizations, which play an important role in training scalability. I think Google has chosen a kind of unique path for scaling up its software, which is through the compiler instead of through many optimizations on the framework level. So the compiler I'm mentioning here is called XOA, and it's going to be open sourced as a standalone project onto the OpenXOA project. So XOA includes many performance critical optimizations, including fusion, layout assignment, and so on. But here, I only want to focus on a few XOA optimizations that are special, that are especially critical to scalability. So a quick background on XOA. XOA is kind of the machine learning. XOA is abstracted for accelerated linear algebra. It's the machine learning compiler that you can use for many different hardwares, and it also can be connected with different front-end frameworks such as TensorFlow, JAX, and PyTorch. So on the high level, XOA gives IR, which is called HRO, an open source that's called stable HRO. So the framework generates a program that's represented in this IR format. And then XOA will be able to do, first is high-level optimizations, which is hardware agnostic optimizations on this IR. And then XOA can translate this IR using different backends to generate programs for different hardware. The IR gives you an expressive yet concise set of operations. There's about 100 operations in the operation set, including control flow operations and collective operations, which like reduce and gather and so on, that lets you do communications between the hardware. And the high-level optimizations transforms the machine learning program based on different kinds of heuristics, trying to improve the performance. And the different hardware-specific backends generate code that runs efficiently on the hardware based on the program that's being optimized. From my point of view, I think there's some unique benefits of using a compiler as a shared infrastructure for scaling up machine learning workloads. One is that with the expressive IR, optimizations can understand global application semantics. This can enable optimizations that target specific scenarios. For example, the optimization may target a specific pattern of the computation and apply heuristic to improve the pattern to make it more efficient. And also, because this is done at the compiler level, once the program is written, the user does not have to know what optimization is happening under the hood. It's very much like you read a Python program and you don't need to know what Python compiler is doing under the hood. User can get the benefit of performance optimizations almost for free. So also like when the compiler implements a new optimization, there's almost like there's almost little to none non-code change for the users to actually take advantage of the new optimizations. And also the optimizations are composable. By composable, we mean that you can apply new optimizations on top of existing optimizations without actually changing the user code. This is because we are transforming programs, right? We can, as long as the programs are valid intermediate representation, the compiler will be able to optimize them. This also provides a separation of concerns for the user. Low-level details such as partitioning communication will be hidden from model developers, and the model developers would only have to focus on the model architecture and mathematics. And also, this also brings that common optimizations that the compiler implements would benefit all workloads without having user involved. So the rest of the talk that I want to focus on, especially three technologies. So one is automatic weight update sharding. The other is GSPMD, which is a general mechanism for partitioning machine learning computation across a large number of hardware devices. And third is pipeline parallelism on top of SPMD. So for weight update sharding, the motivation came from data parallel training. Back in the days, data parallel training is the most dominant use case of TPU and the most common training scenario, I guess, like both industry and in academia. So when you scale up data pilot training, there are 4 components, or like there are four portions of tasks in a training step. So there's forward propagation, then you do back propagation to generate the gradients. Then you do or reduce to sum up the gradients, and you use the gradients to update the model weights on each of the training device. When you scale up the training, so both the forward propagation time and backward propagation time would reduce because there'll be less and less data for each device to compute. However, the weight update time remains constant because the number of parameters on each device is always the full model. So you always have to update all the model parameters on each device, which means that weight update time remains constant. When you scale this to a very large scale, weight update actually becomes a bottleneck. So this is the motivation to introduce weight update sharding. So basically, the idea is we can shard the weights across the devices, so that when weight update happens, each device only have to update its local portion of the weights, and when weights are needed in the next iteration for computation, there will be an all gather that actually gathers the weights from other devices. So the all reduce here actually becomes reduce scatter, where each device only receives a portion of the gradients, a portion of the synchronized gradients that corresponds to its local parameters, and the total communication cost of the all reduce is not changed. It's still the same as doing all reduce when we do reduce scatter and all gather. But this allows us to reduce the weight update cost when we scale up the data pilot training. So this was SPMD. Sorry, this was weight update sharding. But like when we scale model size to larger and larger, weight upsharding or data pilot training does not solve the problem for us, because one is each input or activation tensor might be too large to fit in one device, or the model weights might be too large to fit in one computing device. So this brings us the question: can we actually partition the machine learning model across multiple devices to achieve model pilot training? So that's when Google started working on the technique called GSPMD to partition the model across many computing devices. So GSPMD introduces annotation style in API for the user. So user can annotate a few K tensors in their program to tell the compiler how the tensor should be sharded. For example, the tensor could be replicated or could be tiled and partially tiled. Tiled means fully divided tensor across all the training devices that's involved. Or partially tiled means you can do partially replicated across some number of devices and partition the tensor into subgroups. So user only have to annotate a small set of tensors in their program, and XAVV automatically propagate the tensor sharding to all the tensors in the program, and then transform the program to a sharded form. This allows TPUs. This allows users to scale their single model training to thousands of TPU chips while achieving high flop utilization. So there are actually some promising work coming from collaborations with academia, such as ALPA, that tries to automatically generate the sharding annotation instead of having users manually annotate them. So So we can also build pipeline parallelism on top of SPMD as a special case of sharding. So pipeline parallelism essentially is that we are running a loop on each pipeline stage, going across different macro batches, so that we can essentially place different layers on different pipelining stages and run the loop across macro batches on each training device, on each pipeline stage. And we use click commute to communicate between the stages. So this can be so that this pipeline parallelism can be achieved as a special case of SPMD sharding. So as you can see over time, we started with large-scale data parallel training and used read-optic sharding to push scalability to limit. And then to push scalability to extreme, but when the model size becomes too large to fit on a single device, we introduce SPMD and pipeline parallelism to further scale the training computation. So yes, this gives us a quick overview of the kind of compiler optimizations that Google has done on XLA. With that, I'll be happy to take questions if there's any questions.
Hey, thank you, Janelle, for also being so early for us from the West Coast. So since this is the last talk, feel free to ask any questions you have.
So I have a question. Janelle, this is Chirong over here. My question, I guess, is less about the XLA stack and more about the fact that Google has this PyTorch front end, but specifically for TPU, right? And I've always been wondering if Google is able to compile that PyTorch down through the XLA stack to TPU, and XLA is ultimately can compile to other type of hardware. What stops Google from forking PyTorch just to create a version of PyTorch that works on XLA, right? I'm a little curious about the reason why we have PyTorch for TPU, but not PyTorch through XLA on other hardware.
So the question is about what stops Google from forking PyTorch, right? So PyTorch is so are you suggesting that maybe it's optional for Google to adopt PyTorch as the main machine learning framework that we use at Google?
Not quite. So the question is really that one of the reasons why the XLA stack isn't that common, even in as it could be, right? Is partly because if you're not running PyTorch on a TPU, if you're running on, say, NVIDIA hardware, then your options are TensorFlow or JAX. But the dominant use case is PyTorch on NVIDIA, right? So I'm just wondering if Google had the technical capability to create PyTorch for TPU, then what stops it from creating PyTorch for GPU on the XLA stack?
I think this is mainly a question of how well XLA would perform or with GPU or so I think this is the more of a question of whether or not people invest put enough investment into XLA GPU side to make all the use cases work well. I think so far XLA has before XLA has been a part of TensorFlow, so it has. But I think what's going to happen is Google is going to open source XLA as a standalone project outside of TensorFlow. Google will try to invite contributions from the open source community into XLA and to be able to connect XLA with different front ends and different backends, so that other users who are interested in different front ends, different backends can contribute and also benefit from this common infrastructure. So I guess so in summary, my answer to the question is, yes, Google is trying to make XA a more general solution for the machine learning compiler, as a machine learning compiler for the industry as well, by making it standalone outside of TensorFlow. Because a lot of people are thinking XA is, it's only working for TensorFlow, which is not really the case.
Gotcha. I do have one more follow-up question on that. Okay,
yeah.
Let's say now let's look to the future, right? If XLA is going open source, what does it mean for competitor projects such as TVM, right? Which kind of occupies that layer between like optimizers and hardware specific backends. Like, do you see like I'm just curious, what do you predict is going to happen when all of these compiler projects start to become open source? And then will it be a fight for dominance? Is there a specific niche that each of them falls into?
Yeah, so I think this is an interesting question. It's of course, like I think different compilers will have their own unique capabilities. Right now, I think we are probably still in the early stage of open sourcing all these compilers and see what it becomes. I think probably one thing is different compilers might have unique advantages for different workloads that they focus on. I think part of the reason that Google wants to open source XOA is to have different people coming from different application domains to contribute to XOA, so that XOA becomes more generally applicable to different workloads. But yeah, so it's hard for me to predict if there's going to be a single winner. I don't think there is strictly a competition of different compilers. It's trying to it's more like trying to serve the common workloads and trying to provide infrastructure for different users. I think currently the students different compilers have their own unique capability, but yeah, we hope to invite general contribution to the compiler for different workloads. So I don't know if that answers your question.
It was insightful. Thanks a lot, Jeanette.
Thanks, Jerome, for questions. Any more questions from the audience? Okay. I guess thanks again for Gina. Yeah, for the talk. I think Jerome will take over announcing a couple of logistic issues. Great.
Okay, thanks a lot.
Okay, goodbye, Gina.